How do I end the live stream? Damn it. How do I end the live stream? Okay, I guess we're live now. We're having too many technical difficulties, so we'll start in a bit. Okay. Seems like we're finally there. Okay, I think let's get started. Sorry for the delay. This was unanticipated. It worked so smoothly yesterday because we didn't really cut through the margins too much. Hopefully it will not happen again. So we're going to start the second lecture on computer architecture, and we're going to continue where we left off. Let me see, actually, I wanted to actually log into Zoom over here so that I can see your faces. And hopefully we will do it hybrid in person, where I'm lecturing in person next week. We'll try to set up everything for that for next week. But let me do this one for now. Okay. Too many messages here. Okay, good. I think I can see only part of the room, but can you guys see me? Okay, good. I think I see some confirmation. We need some wider screen cameras here. Okay, I think let's get started. So we're going to continue where we left off yesterday, where we were talking about some interesting trends, trade-offs, and issues in computer architecture. And we're also going to touch upon fundamentals today. And hopefully my intention is to give you the course logistics at the end also. So let's see how much we can cover. By the way, I see on Zoom people being admitted. If we could turn that off, that'd be great, because I don't want to see whenever someone is in the waiting room every time they come in. Okay, so as I mentioned yesterday, we were talking about many interesting things that are happening in computer architecture. And I've given you some examples yesterday on machine learning accelerators, processing in memory, genomic accelerators, non-volatile memory. And today we're going to continue that a little bit. And these are all topics that we're going to go in depth in the course. I'm giving you some higher level perspective right now so that you can get a broader perspective before we go deeper in each topic in this course. And I'm going to give you a higher level perspective of an important issue that's happening in computing systems. That's reliability, security, and safety. And these are critical problems in computing systems today. How do we build essentially more robust systems? And robustness is a nice word that captures reliability, security, safety, and to some extent privacy also. But these issues are becoming increasingly important as technology scales and as we rely more and more on computing devices in our daily lives. And that's happening with self-driving cars, for example. So that certainly leads to reliability, security, and safety issues, in general, robustness issues. You can also think of these as dependability issues, right? You're depending on computers. And if they're not measuring up in terms of dependability, then you're going to have issues. And reliability problems, security problems, safety problems, and predictability problems all affect dependability in the end. You can hear me fine, right? Okay, good. If it's too loud or something, let me know also, because sometimes the microphone comes too close to my mouth over here. Okay, this is a very general problem, clearly, and we will see examples of this in this lecture, but I will mention one important issue that was mentioned yesterday also, which is RowHammer that we have been working on. I think this is a fascinating issue to look into in computer architecture because it's fundamentally a device and circuit level problem. And that has percolated into all the way into the software stack, essentially. So basically, you get bit flips in modern memories if you have a particular access patterns. And those bit flips certainly corrupt your data. They lead to reliability problems. And they also can be exploited to take advantage of them so that someone can take over your system, for example. Someone can launch an attack where they can leak your data or take over your system completely. And I think this is fascinating because something like this has not been demonstrated for as long as I think computers have been around, at least to this extent. Let's say you have a bit flip at a circuit level and entire software stack becomes vulnerable. How many of you know about RowHammer, by the way? Can I have a show of hands? Okay. Oh, there are quite a few who, well, it's somewhat. Some people say somewhat I know about it. That's good. That's good. So as I said, people come into the course from very diverse backgrounds. So we'll cover RowHammer in more detail. But to give you a high-level perspective, essentially, it's the fact that you can predictably induce bit flips in commodity memory chips, DRAM chips. And DRAM chips are employed in almost all computing devices today. Your cell phone has a DRAM chip. Your laptop is a DRAM chip. Any general purpose computer has a DRAM chip. Any special purpose computer also has a DRAM chip. There are very few exceptions, basically. And when we did the studies for the first time in 2012 or so, we found that more than 80% of the tested DRAM chips were vulnerable to this problem. Basically, you can predictably induce bit flips. And first of all, inducing bit flips is bad, but predictably doing it leads to security problems because an attacker can now figure out how to induce these bit flips at the right time, in the right place, and take over the system. And again, we're going to go into more detail of this in later lectures so that you can understand the scope of something like this in computer architecture and also system security. But this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And you can also read articles that are much, much higher level than this course that talk about essentially forget software. Now hackers are exploiting physics. And I think this is a nice high level explanation about RowHammer. So let me give you the fundamental problem very quickly. I'm not going to go into a lot of detail because we will have lectures dedicated to this and also the cutting edge here. But essentially, the problem happens because you're activating one row and applying high voltage. And the activation that you do in this row, and this is a row of memory. If you remember your basic computer architecture class, memory consists of rows or word lines, let's say. And also you have bit lines, which are not shown here. And a row contains memory cells. In DRAM, it could be 8K memory cells, for example. When you activate all those cells by applying high voltage to the word line, that activation you're doing is disturbing the cells that are around. This is due to essentially electrical disturbance because things are not isolated well enough from each other electrically. And what you're doing in this row is causing disturbance in adjacent rows and perhaps even farther rows also, depending on how close the rows are to each other, how small the cells are, and how the wires are connected and how strong the voltage is, of course. So basically, each activation or applying high voltage to the row causes disturbance. And if you do it repeatedly, activate, precharge, activate, precharge, activate, precharge, activate, precharge, activate, precharge, and DRAM, meaning high voltage, low voltage, high voltage, low voltage, high voltage, low voltage. It turns out physically adjacent rows can get bit flips. And this should not happen clearly because you're not even writing to memory, right? You're just activating memory so that you can read from it. You're not even reading from memory in this particular case. But just because you're activating a row, the disturbances you cause because of those activations are causing bit flips. And when we wrote the paper, we call this a hammered or aggressor row, and we call these the victim rows. And the victim rows can be far away also, like slightly far away. So you may actually get bit flips in this second physically adjacent rows as well. It's less likely, but it happens according to our studies. So the problem is getting worse also because cells are getting smaller and people are trying to pack more cells within a given area so that you can increase the DRAM capacity. That's the idea of technology scaling, right? Okay, we'll talk more about that clearly. But basically, RowHammer is the fact that repeatedly reading a row enough times before the memory gets refreshed induces this sort of disturbance errors in adjacent rows in most real DRAM chips you can buy today. And this was, today was 2014 or so. But actually, that's true today also. We will talk about some of the cutting edge research from 2021 that's going to be published in a few weeks later in this course. And you will see that this problem has not gone away. Even though people have applied mitigations, their mitigations turn out to be not secure enough to prevent this problem. And we can discuss why that is the case. Yesterday, we briefly discussed why that may be the case, right? Because one of you had a good question about this. But we can discuss in more detail why this has not worked. The mitigations have not worked in industry, at least, when we get to RowHammer in more detail. Okay, I think this is fascinating. Hopefully you find it fascinating also. And this is data from this paper that we published 7 years ago. And we found out that more than 80% of modules that are manufactured by 3 major DRAM manufacturers are actually vulnerable. And if you don't know the memory industry is dominated by 3 major manufacturers today: Samsung, Hynix, and Micron. And all of their chips are vulnerable. So it's not a problem particular to one company or one type of DRAM, let's say. It's really an industry-wide problem that is caused by the fact that we have pushed technology scaling too hard, let's say. The cells are too close to each other. Cells are too small. They're very much vulnerable to this sort of disturbance effects. And as a result, you're getting these bit flips. Okay. Is everything okay? I see people looking at one side over there. Okay, maybe I'll continue unless someone speaks up. Okay, and this slide over here shows that this is a technology scaling problem, as you can see over here. Chips that were manufactured before 2010 actually don't exhibit these bit flips. But chips that were manufactured in 2012 and 2013 all exhibit these bit flips. Meaning in older chips, you cannot do enough activates within a refresh interval to cause these bit flips. But newer chips, cells are closer to each other, cells are smaller. As a result, you can do enough activates to actually disturb the cells and cause bit flips. Okay, so this is very interesting, and we're going to go more into it. It's fascinating because it's a reliability problem, but it can also be exploited for security. And when we wrote the paper, the first sentence we said was, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. So in the end, what this sort of disturbance is causing is it's breaking memory isolation between different memory addresses, right? Your memory addresses should be isolated from each other. When you do something to memory address A, memory address B should not be affected. That whatever you do, regardless of whatever you do to memory address A, right? But here, clearly data is getting corrupted, breaking this isolation property. And as a result, this can be a reliability problem and also a security problem. It's also a security problem because someone can take advantage of these bit flips to do various things. It could be certainly to just corrupt someone's data, right? It could be to take over the system such that you can have full permissions to the system so that you can get access to any data, you can run any program. And that's exactly what the Google Project Zero blog post and Black Hat presentation actually showed after we wrote our paper. And we're going to go more into detail about that in later lectures. Right now, I just want to introduce this topic. And people also make interesting analogies. Let's say this famous hacker on the internet said it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. And this is also getting to the disturbance effect, right? You're actually causing vibrations or perturbations by actually doing opening and closing the door, let's say, repeatedly slamming the door. Okay, again, I don't want to spend a lot of time on the details of RowHammer. We're going to have more lectures, but just to give you an idea, there have been a lot of attacks that clever people developed over time to take advantage of these bit flips such that they can, for example, gain unrestricted access to systems of website visitors by taking advantage of JavaScript. They can gain control of your cell phone, for example. This is actually very interesting. These folks released an app, an Android app, that essentially figures out which bits in your cell phone memory are vulnerable to RowHammer. and it basically hammers your phone. And I would encourage you to take a look at it. Some of these papers may be actually recommended readings later on. People have shown that you can do these attacks using GPUs. We will cover GPUs partially in this course later, but you can see that a GPU has a lot of power because it has a lot of cores. You can actually do a lot of accesses to the memory at the same time, meaning that you can actually do a lot of activates, a lot more activates than you could do in a CPU, for example, in a multi-core CPU. So you can accelerate these attacks when you actually do them with a GPU. And you can also do these attacks over the network through the RDMA, Remote Direct Memory Access engine. These folks also did the same thing. You can also leak private data. So even if you cannot take over the system, these folks show that you can leak data that's private, which is a limited attack, but still, you don't want to lose your private data, right? And there are more recent works that, there are many, many more attacks that I'm not going over, but there are more recent works that are actually quite interesting also. These folks show that by doing RowHammer attacks carefully, you can essentially destroy the accuracy of neural networks. So your neural network, this is another paper that does something similar in a different way, but your neural network may be good enough, let's say, your accuracy may be 90% for inference tasks. For example, let's say pedestrian detection, right? You're running pedestrian detection in your self-driving car. You're reasonably accurate. I don't think 90% is good enough in this case, depending on what metric is 90%, but let's say 99%, fine. If someone attacks your neural network accelerator and causes RowHammer bit flips, your accuracy can go down to 10%, according to the results of this paper. And this is just one result, basically. And this sounds pretty bad, of course, right? Okay, there's one question. Let me see. So what actually inspired the research that led to the discovery of RowHammer? Was disturbance in DRAM already a known effect? So this is a very good question, actually. So disturbance in DRAM, actually disturbance in memory is a very well-known effect for a very long time. I mean, even the first DRAM chip that was manufactured by Intel in the 1970s was vulnerable to disturbance errors. It's not exactly like this sort of disturbance, but there was disturbance between the bit line and the cell, for example. So they had to move the cell from the bit line away a little bit so that they can reduce the disturbance. But disturbance in memory is very general. Read disturb errors in flash memory was, for example, very well known. And it was also clear to people who actually knew the error mechanisms in memory that there would be disturbance in DRAM also. So no question about the existence of disturbance, and that's a very well-known effect. Now, what RowHammer differs is that these disturbance errors became really viable through software. Essentially, normally you have disturbance effects and you somehow mitigate them, right? Your refresh rate is good enough so that you don't have these RowHammer problems. But because of technology scaling, it turned out, well, we had the hunch together with Intel when we were doing the research that these will actually become visible to software at some point if something is not done about it. And that's what really inspired the research that we were doing on it. Basically, with RowHammer, these disturbance errors started happening through software, meaning you could actually induce these disturbance errors within a refresh interval in DRAM, and there are no other correction mechanisms. As a result, these bit flips directly get exposed to software. Now, that's a huge problem, clearly, because it affects your reliability, it affects your security, and it affects your safety. So hopefully that answers your question. I think disturbance was under control until RowHammer showed that it was not under control, let's say. Or people didn't take the right measures to actually keep it under control. So we will get back to it when we actually talk about RowHammer in more detail. Maybe there was a potential way of keeping it under control, but maybe people didn't think about it as much, right? And going forward with technology scaling, we cannot afford that. People should think about these reliability, security, and safety issues, or any bit flips that may be happening, and they should actually plan for it. Essentially, this is really the status quo going forward. We're going to have a lot of reliability issues, and if you cannot ignore them, basically. Okay. So that's very good. So this is the paper that we wrote that introduced RowHammer in 2014. We will have stories about it when we talk about RowHammer in detail. And this is a more recent paper that we were invited to write. And this actually gives a very good coverage of RowHammer research until 2019. But a lot has happened after 2019 also, actually, which I will briefly cover. Now that you're taking this course in 2021, you have the nice hindsight of what happened in 2020, right? This is a paper that we did to revisit RowHammer. And basically, we showed that RowHammer is getting much worse today. Newer chips, and many chips are vulnerable to RowHammer. Newer chips are much more vulnerable. And if you turn off the RowHammer mitigation mechanisms that are employed, there are some chips whose weakest cells fail only after 4,800 activations. So if you do that high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, only 4,800 times. That's not a lot, by the way. Today, within a refresh interval, you could fit more than hundreds of thousands of times activations. But these bit flips are very easy to induce, basically. So at the device level, technology level, the problem has gotten much worse because cells are smaller, noise is higher, and cells are closer to each other. And the device level solutions are not really talked about in the literature. The manufacturers, even if they're employing any device level measures, I don't believe that they're doing that as much because that affects their cost significantly. They're not really talking about it, basically. Okay, there's clear indication that spatially RowHammer is becoming worse also because you can induce bit flips in more rows and farther away from the victim row as well. And it turns out existing mitigation mechanisms are not effective. This paper also shows that with analysis of more than 1,500 DRAM chips. So we're going to talk about this in more detail. And I think this is really fascinating. This is also fascinating because it bridges the gap between circuits, architecture, as well as software, system security. So it touches upon a lot of topics in the computing stack, if you will. We're going to talk about mitigation mechanisms also. I'm not going to touch upon that in this introductory high-level lecture. But I will mention another work that we have done in 2020 in collaboration with Kaveh Erzavi, who's also a professor right now at ETET. But we showed with this work that existing, so what the DRAM manufacturers did after our work initially in 2014 was they said that they fixed the problem. They basically introduced some mitigation mechanisms inside the DRAM. They didn't tell what it was. At a high level, it was refreshing some adjacent rows, basically, but they didn't tell exactly how it worked. So they were obscuring the security mechanisms that they employed in their devices. They said that they fixed the mechanism. In fact, some of the DRAM manufacturers said their chips are RowHammer free. And basically, in this paper, we proved that that's not correct. Basically, this paper showed that you can reverse engineer the internal mitigation mechanisms that DRAM manufacturers employ inside their DRAM chips just enough so that you can actually create some custom access patterns to DRAM that would circumvent those mitigation mechanisms. And we're back to square one, basically, because of this. So mitigation mechanisms are not secure. But I think the approach taken to secure DRAM was not good also from the industry perspective, let's say, because they were a little bit hush-hush about it, let's say. And security by obscurity in general is not a good idea. If you want to be fully secure, you want to really propose your security solution and say, okay, here's my solution. Here's how it works. Attack it. And let's prove that it's secure. They didn't do that. They basically said, oh, we have some mitigation mechanisms and it's free. They didn't really consider, let's say, the creativity and the power of people who can attack those mechanisms. But if you're much more open and if you actually propose a solution and say, okay, attack it and let's make it secure, then you can make you can create a much more secure system from the beginning. So that's why we're back to square one, and let's see how things will evolve from this point. Okay, there are other works that I'm not going to talk about right now, but we will talk about when we get to RowHammer in more detail. It's fascinating. This is a work that we did with Microsoft Research to figure out whether you can qualify a DRAM chip to be RowHammer free or not. And the answer is no. It's very difficult, basically. And we'll see why the answer is no, maybe when we get to it. Of course, there are solutions that are developed also. I'm not going to talk about the solution in detail, but one solution that was employed in Apple systems and many, many other systems is to increase the refresh rate. Basically, by increasing the memory refresh rates, you're reducing the number of activations you can do within a refresh interval. So basically, if you can refresh the cell before the charge gets depleted due to RowHammer, then you save the problem, right? You solve the problem. So people increase the refresh rates. Clearly, there are a lot of downsides to increasing the refresh rates. Refresh basically means you read your memory periodically more often, and just to do the refresh, just to refresh the memory. We're going to talk about refresh in one of the lectures soon also, so you will get an idea about it. So you don't want to increase the refresh rates to solve a problem like this, but people do it, and it's not clear how secure it is, because our paper, or our original paper, showed that to make DRAM fully secure based on what we have tested, you really need to increase your refresh rates by 7x. And I think that number has gone up by now. It may be actually 16x right now, 16 times. So instead of refreshing every 64 milliseconds every row, you may need to be refreshing every row every 4 milliseconds or so. Clearly, that's not good for performance and energy, but people have increased the refresh rate by about 2x and maybe 4x, because some DRAM chips also internally increase their refresh rates according to our experiments. Okay, but there are other solutions also. This BlockHammer solution is something we're going to talk about when we get to RowHammer. This is an example of co-design of the memory controller and the DRAM chip. Basically, inside the memory controller, you can take action such that you can reduce the probability of hammering the rows. So you can basically detect which rows can be are being hammered potentially, and then slow down the accesses to those rows, throttle down the accesses to those rows. And I think this is a good solution direction. There are other solution directions that I'm not talking about right now, because that's not the major focus of this particular lecture, but we will cover some of these solution directions. And I think this is fascinating because your solution directions actually can span the entire stack. This is one example of issues that you can solve in the software level also. People have proposed, for example, using performance counters at the software level to detect which rows are being hammered. And there are papers published related to it. I think this is an interesting solution to explore. I think it's a bit dangerous because relying on performance counters at the software level has a lot of overhead in terms of both performance, and also potentially maybe missing some row activations when you rely on performance counters that are not necessarily robustly architected inside your system. But we will talk about these solutions also. But keep in mind that solutions can be at the device level, at the circuit level, at the architecture level, at the logic level, at the software level, at the system software level also. But we'll talk about that later. Okay, if you're let's say impatient, you can certainly look at lectures that we have already online, and this could be a foreshadowing of what's coming. But keep in mind that the lectures that we will do in this semester is going to be more up to date, because these old lectures do not cover some of the most cutting edge research in the topic. And there's an old talk that I have delivered on the topic as well. Okay, so that's RowHammer. Let me talk about 2021. That's the cutting edge. So Google also recently introduced, I think this was May, as you can see over here, 2021, a new RowHammer patterns that they claim to be not handled by mitigation mechanisms. And this is also an interesting read. I would recommend taking a look at it if you're interested. So Google has been doing a lot of research in this area also. And this is our research that's coming up in Micro conference in about 3 weeks or so, I think 2 to 3 weeks. And here we actually look at different ways of improving the access patterns in RowHammer, showing the temperature dependence of the cells, showing the dependence of the activation rates, and also how long you wait for a row to be activated. So you can basically construct, and the spatial variation, you can basically construct much better RowHammer attacks if you really understand what's going on in the sensitivity of the cells for different effects on RowHammer: temperature, spatial location, as well as how long you can keep the row active. And it's very fascinating. I think there's more research to be done in this area. And again, if you're fascinated about it, feel free to approach us about doing research, because as you can see, we're doing a lot of interesting research. There's another work that's coming up at Micro that's along the lines of trespass. Basically, we have further understood the in-DRAM RowHammer mitigation mechanisms that are employed by DRAM manufacturers. And right now, we can actually reverse engineer almost all of the mitigation mechanisms that they have in their chips from 3 major manufacturers, 45 DRAM modules. And this leads to some very interesting customized RowHammer patterns. So this actually introduces a methodology to enable you to reverse engineer what's happening inside the DRAM chip to protect against RowHammer. And the insight is that by by inducing data retention errors in DRAM, you can figure out how the internal mitigation mechanisms are working. And you will see how that works when we actually talk about it in more detail. But I think this is a very clever insight that enables very interesting, newer, and much more powerful RowHammer attacks. And I think this also shows that whenever you approach a system, and if you want to make it fully secure, basically don't go and just say, I just did something and it's secure. Basically, prove its security first. And proving its security, I think the methodology that I mentioned earlier is work with other people who are experts in security so that you can actually prove the security of a mechanism. And I think all of this is happening, like this paper clearly shows that because people did not prove the security of in-DRAM mitigation mechanisms, some other people can clearly, with some effort, overcome those mitigation mechanisms relatively. I don't want to call it relatively easily, but because clearly this required a lot of work, but relatively easily in the grand scheme of things, right? If something was fully secure, then we shouldn't be able to do this, clearly. Okay, so basically the takeaway over all of this, not just trespass, but all of this research is RowHammer is still an open problem. Security by obscurity is likely not a good solution. Okay, any questions? I took a little bit longer than I expected on RowHammer, but I think it's good. It's a good foreshadowing of what we will cover, and you may have more questions and insights and potentially solution ideas because we're very much in need of good solution ideas in different directions for problems like this. And I picked on RowHammer because RowHammer is a specific example of what's known more generally as fault attacks. People have looked at what's called fault attacks. Essentially, you induce a fault, hardware fault. It could be a software fault also, but let's say a hardware fault. And you basically trigger the attack based on that fault. And that fault can be a single bit flip. That fault could be something else also, potentially a failure of a DRAM chip, right? Complete failure of a DRAM chip. But a bit flip is usually easier to exploit. And RowHammer is a very nice example of a fault attack because it can be controlled. It can be done by the software. It can be done at the user level. So older fault attacks assume too much, basically. They basically require physical access to the computer and maybe some privileges that you don't normally have. The beauty of RowHammer, or the scary thing about RowHammer, is that anyone can do it at the user level through software. As people have shown, you can do it over the network. And you may not be, unless somebody is really looking to detect you, you may not be detected while doing it. Okay, so hopefully that's clear. I don't see any questions, but feel free to, yes, I see one question in the room. Yeah, feel free to speak up. You can press and see, or however you would like to do it.
Yeah. So a question first is, you said the required refresh rate has gone up. Is that just because cells have gone closer and they're more noisy? So now with by hammering a single row, you can go and access more rows at once?
That's right, exactly. Basically, cells are closer, things are more leaky, and noise is higher, and also cells are smaller at the same time. As a result, the number of activations you can do to induce a single bit flip has reduced significantly.
And another question is, does your lab focus more on sort of like the white hat hacking, or on like creating like the mitigation systems? And if you lean towards a certain direction, why would that be?
Oh, that's a good question. So I think I would say both, basically. I think you need to, as security researchers, you need to do both, in my opinion. You need to understand the attacks very well, and also you need to develop defenses. So we have both. For example, we'll talk about the original RowHammer paper more when we talk about more RowHammer later, but you will see that that paper shows the security problems, but it also proposes solutions. And in fact, some of the solutions were employed in industry, but unfortunately they were dropped a little bit because DRAM manufacturers claimed that their DRAM was RowHammer free. Cool. There's another question.
If RowHammer is that bad, why are manufacturers not taking it seriously?
I wouldn't say they're not taking it seriously. I think they're taking it seriously, but They don't, in my opinion, there's a problem with the DRAM industry in general. It's very much commodity driven, and it's very much cost oriented. So a lot of these things are not, let's say, maybe you're right. Maybe they're not taken as seriously as increasing the capacity of the DRAM chips, right? And I think that mindset needs to change. Basically, that's what we're trying to point out. So I think we will talk about this more when we get to not just RowHammer, but also processing in memory, for example, right? Processing in memory has not been enabled for 50 years, even though there were very good arguments for it. But finally, manufacturers are trying to enable it. Maybe the manufacturers are not good at understanding the security implications of what they design, basically. I think that's my best explanation to it. Plus, there are business implications, of course. It increases their cost. And also, the DRAM interface limits what you can do today. We'll talk about all of this. The solution can be done by the manufacturer. The solution can be done by the system. For example, initial solutions were introduced by Intel to employing the memory controller. This is the solution that I mentioned that we developed in our paper. Intel actually adopted it in their memory controllers. But then manufacturers took it seriously in some sense, and they said, okay, we developed a solution. So you don't need to do it in the memory controller. But then their solution was not good enough, right? So I wouldn't completely say that they're not taking it serious. They're taking it seriously, but maybe they're not doing a good job in solving the problem. And again, I think sorry, go ahead, please.
I was just saying thank you.
Okay, sure. Thanks. I will add one more comment to it. It's also that it's not an easy problem. Well, it's an easy problem if you know how to solve it, but it's not an easy problem if you don't know how to solve it, right? Because technology scaling has created this problem clearly. And there are no easy solutions if you're really used to just reducing the size of your cells, right? Okay, that's why I think architectural solutions are actually very, very interesting to explore, and we will cover them later. Yes, there's one more question in the back.
Yes, I was wondering, when you say that RowHammer is still an open problem, does that mean that if I rented a virtual private server at one of the big providers, could I RowHammer that server, or do they have mitigations in place?
Could you say again, big providers of like cloud providers?
Virtual private server, I mean, any cloud server, if I rented one.
Oh, okay. So that's a good question. We don't know, basically. I think people actually, if you look at what's happening in industry, I'll give you more insight about what's happening in industry based on the research that has been done in the last year. But especially those cloud providers got really worried based on the results that we published in 2020. And they basically said, we need to solve this problem. So they actually formed task groups recently in 2020 to actually solve the problem. That's why Microsoft research is quite involved. Google research is quite involved in this. And they don't necessarily also know, basically. So usually cloud systems, depending on which cloud system it is, they employ ECC, error correcting codes. But our papers also show that they're not enough. Error correcting codes are not enough, basically, to solve the problem, because you can get more than 2-bit flips in systems. Okay, cool. These are very good questions. So we're going to cover more, think more questions until we get to it. Okay, so I'm not going to talk about Meltdown and Spectre as much. How many people have heard about Meltdown and Spectre? I assume many more. Yeah, because these were publicized quite heavily. But these are essentially issues at the microarchitectural level. Because of the design of the microarchitecture, your system is also vulnerable to leakage of information. This is a bit different from RowHammer. RowHammer is really a bit flip, right? It's a fault attack. But these are more side channel attacks. And I'm going to give a high-level overview of this, not detail. We're going to have some papers potentially assigned to read later on. But basically, someone can steal secret data from the system, even though your program and data are perfectly correct. Your hardware behaves according to the specification, which is not the case in RowHammer. In RowHammer, you should not get bit flips, for example. There are no software vulnerabilities or bugs, basically. And the idea is basically, why does this happen? People have found out that speculative execution, like branch prediction and executing on the wrong path of an instruction stream, leaves traces of secret data in the processor's cache. You may actually load some data that gets stored in the cache, which is part of your lab 1, which is an internal storage in DRAM that's not internal storage in the processor that's not visible normally to the outside. And someone can actually, basically it brings data that's not supposed to be brought accessed if there was no speculative execution, because you may actually go out of bounds of an array, for example. That's possible in wrong path. And a malicious program can inspect the contents of the cache to infer what that secret data is. And it's not supposed to access this data. So a malicious program can be running concurrently with some other program, some important program that's actually accessing privacy critical data, let's say. And that program brings some data, executes on the wrong path, and brings some data into the cache. And the malicious program, by doing what's called cache timing attacks or cache side channel attacks, can infer what data is being accessed by the program it's co-running with. This is not an easy attack. This is actually much harder than RowHammer, in my opinion. And that's true for many, many people think that way also. Because you need to, first of all, align your malicious program to run concurrently with another program that's accessing security critical data that you care about. And you also need to make sure that you can time the attacks. You can time the accesses that are made by the program that you're running with, the security critical program, let's say. And the timing differences between the accesses provides a side channel of what data values are being accessed by the security critical program. That's at the high level description, of course. If you want to go to the low level, there's a lot more detail than this. But that's the idea. Again, it's not easy to do. And also, I don't know why my computer is a bit slow, but yeah, basically a malicious program can actually force another program to speculatively execute code that leaves traces of secret data. That's also very interesting. The way you do it is by basically polluting the branch target buffers and branch prediction structures such that the other program that you're running together with gets branch mispredictions more often at the right times. Okay. Again, I'm not going to go into the details of it because clearly this this covers a lot of issues in microprocessor design, microarchitecture. But people have shown that you can actually do these very sophisticated attacks. Meltdown is a little bit different from Spectre. Meltdown is easier to solve. I'm not going to get into it, but Spectre is really fundamental to how speculative execution works. People have not really solved Spectre, in my opinion, yet, although Meltdown is easier to solve. This was, if you're interested in reading more about it, but if you're reading more about it, you can read this nice blog post by one of the discoverers of this attack, Jan Horn from Google Project Zero. There's also another paper related to Spectre and another paper related to Meltdown that you can easily find online. But basically, this says what I said. Let me read it very quickly, I guess. We have discovered that CPU data cache timing can be abused to efficiently leak information out of misspeculated execution, that's wrong path execution, leading to, at worst, arbitrary virtual memory read vulnerabilities across local security boundaries in various contexts. It's a bit cryptic, but basically it's you can leak information across local security boundaries. So in a sense, it's not as bad as RowHammer, because RowHammer leads to someone taking over your entire system. With Spectre and Meltdown, I have not seen anybody showing that they can take over your entire system, because you cannot cause bit flips, right? You can just read and infer what the data is. Whereas RowHammer is, in a sense, much worse, because by causing bit flips carefully, someone can take over your system. In this case, you lose some private data, but maybe you keep your system secure. Okay, we will talk hopefully more about Meltdown and Spectre also, but let's see how much time we get. But if you're interested in this, this is also fascinating. And this is also relatively cutting edge that's happening. And we don't have a solution fully to Spectre yet. People have explored solutions. For example, turning off speculative execution is a solution, right? Clearly, you don't speculatively execute. You never mispredict a branch. Well, that's clearly a solution, but that's a very bad solution, because that really destroys the performance of a pipelined out-of-order processor. And people have really improved speculative execution to get high performance for decades and decades. If we want to revert back to, let's say, 2x, 3x lower performance just for this security, that's probably not a good idea. My opinion is that we need some other solutions. Like whenever you're executing security critical applications, maybe you should really not be running together with someone else, right? I think there's an easier solution to this problem. But I think jury is still out. Basically, people are trying to find a balance between the performance that you get out of speculative execution and the security holes that it's security or side channels that it creates. And later, actually, research showed that it's not just speculative execution, but a lot of the choices that you make in the microarchitecture of a processor that is related to instruction execution and that affects the timing of different instructions in a data-dependent manner can significantly lead to side channels. So anytime you can take, anytime an instruction can take different times based on a data value, and you can measure it, you can potentially create a side channel. Yesterday, for example, we discussed power management related attacks, right? Current management related attacks. If you're executing a power hungry instruction, you need to slow down some other process or some other thread or some other core. And this creates a side channel because you can see the timing difference when you execute with or without the power hungry instruction. And again, I would recommend attending the October 4th seminar by Javad, who talks about the current management mechanisms. In a sense, these are very similar, except Meltdown and Spectre are exploiting speculative execution, whereas the iChannels work that Javad will present is exploiting current management mechanisms. But these are all microarchitectural design choices that you make to improve performance or manage power, and they're creating side channels or covert channels inside the system. And if someone can actually be smart enough to exploit that covert channel, you can lose your private data. Right? Okay, so hopefully that's interesting. Any questions? I can go on and on in more hardware security issues. Maybe we'll have more detailed lectures on hardware security if people are interested in it. But right now I will stop. Okay, so I mentioned this yesterday, but I want to talk a little bit more about more demanding workloads. And this, because this is very important. Workloads have become a lot more demanding because of the deluge of data that we can generate in systems today. And existing systems are not dealing well with the data. So applications are increasingly demanding. And this is my phrasing of it. Dream and they will come, basically. There's an anecdote here that I should say. When one of the earliest pipeline processors was designed, well, not earliest, but popular pipeline processors was designed, MIPS R2000 in 1980s. Some people were saying, okay, this is good. This has good performance. We will never need more performance than this. Well, clearly they were wrong. Right now, the performance of existing systems are more than 3-4 orders of magnitude higher than MIPS R2000. And the reason is basically if you ever make a comment like that, we don't need any more performance, then you're basically commenting on creativity of people, let's say, or the ability to dream of people. And people have dreamt a lot, and they were able to come up with many applications. Neural networks is one example of this, but clearly there's virtual reality. There's what GPUs are very good at, physics and simulation and other things like graphics, clearly. But as applications push boundaries, computing platforms will become increasingly strained. And that's always been the trend. And I think that's not going to change, basically. We all have, as humans, we have increasingly important problems to solve. And they require a lot of data. And these problems are actually fundamental in science, technology, engineering, as well as our daily lives, right? We all want to solve the climate problem, for example, or the congestion problem that's affecting many big cities today. But the solutions may, or weather problem, right? Even weather prediction is not a solved problem today, for example. And these applications are very much data intensive, and applications are increasing. One particular application that we will cover more later is genome analysis. And genome analysis is interesting as for many reasons. As we discussed yesterday, you can actually make better medical decisions, better health decisions, understand the diseases better, etc. And also understand fundamentally how species are related to each other, for example, understand the drug interactions better. And data is really increasing in genome analysis. So this is one device, Oxford Nanopore. This is an older version from 2014, as you can see in the, well, it doesn't say 2014 here, but it's from 2014. But basically with this device, you can actually sequence someone's genome, your own genome, actually. Of course, you need to have the setup for it, but it's relatively cheap. It's like $1,000 or so, I think. The problem is processing of the data is really what bottlenecks you. Sequencing is not a big bottleneck today, but the processing is very much a bottleneck. And this is one example. And if you're interested, you can read this paper, but we're going to cover this more later on. And this is a slide that I used at the beginning of 2020, actually, in my digital design and computer architecture lecture, when I think I first used in February 2020, while COVID was actually really early, let's say, especially in Switzerland. But basically, these devices were being sent all over the world, in this particular case to China, to really understand the spread of the disease by doing genome analysis on humans as well as the virus, right? So this is one case study of why genome analysis is important. It could enable us to understand how a disease spreads, how it mutates, how it affects different methods for fighting with it, etc. And I think there are other applications of genome analysis. One is like if you have a crowd that looks like this, for example, how do you analyze genomes for good, of course, right? Basically, can you actually look at what kind of microbiomes exist in an environment and then predict whether something will cause an outbreak or not? What kind of bacteria is there? What kind of organisms are there? And how do they interact with each other? And how do they interact with people? And this is actually a very interesting study that was done in 2015, city-scale microbiome profiling, to understand what kind of, let's say, species are there and what they may cause potentially for the spread of disease. You can see that this is somewhere in the subway system. I think they're collecting data. Okay. So that's one example, but there are other examples. You can rapidly do rapid surveillance of outbreaks. Ebola was earlier than COVID, clearly, and people actually had portable genome sequencing devices to really understand what's going on. These devices, as they become more powerful and smaller, you can actually do many, many more things with them. And these are some papers that I'm putting as examples. And these are actually very, very interesting papers if you get the time to read them. They show you the power of genome analysis in real applications like Ebola surveillance. But they also show that the data analysis techniques that we have today are not efficient enough, basically. It takes very long to actually analyze the data and come to conclusions. Sometimes it takes weeks, and that's clearly not acceptable in life-critical situations, right? You don't want to wait for weeks if your life is threatened. Okay, so this has all been enabled by technology. So technology is very interesting, right? We've been talking about technology scaling in terms of memory, and we've been talking about the problems of technology scaling, like RowHammer. Refresh is another one we briefly mentioned, but we're going to mention more. But that technology scaling has enabled us a lot of good things also, right? We have high capacity memories, very powerful compute units, but the technology scaling is also happening in the genome sequencer level. So I'm not going to go into the details of genome sequencers, but these sequencers have become much less costly and much more powerful, higher throughput, because the technology that's used to sequence the genomes, whether it's light-based, like in Illumina, or whether it's nanopore-based, like nanoscale holes, as you reduce the size of them, size of the, let's say, the unit that you employ in the technology, you become higher performance, higher throughput, you become highly parallel. And as a result, these systems become much more powerful. So technology scaling is happening not just in computers, they're also happening in these sequencing devices, for example. I think that perspective is really important. And also you can potentially see a sequencing device as a computer. It's not a computer, it's really a data collection engine right now, right? You're really taking something that you want to know and passing it through a device that understands what it is, essentially. And then maybe you need to add data collection, data processing units inside these devices as well. Okay, we're going to talk more about genome sequences, but I wanted to give you the perspective of this technology scaling. And because of technology scaling, now we can actually generate a lot of data, genomic data. But again, the bottleneck is really how do we process it? And these are two example papers that I mentioned in the last lecture also that show how you can potentially go about keeping up with the amount of data that's being generated in genomics by doing acceleration using FPGAs or in memory of genome analysis. Okay, this is an example. This is old data, but you can see the number of genomes that are sequenced in the world. This is increasing. I believe it's exponentially increasing, but I don't have the recent data, so don't quote me on it. But you can also see the effect of technology scaling. So Moore's law is this one. So basically, this is time on the x-axis, and this is the cost per raw megabase of DNA sequence. And they plotted the Moore's law in terms of the trend. That's the transistor cost, of course. But basically, the cost of a single megabase of DNA sequence is reducing much faster than the cost of a transistor is reducing. So technology scaling is actually happening much, much faster and much better in genome analysis today. And that's why this is a problem, right? You have two trends. I don't want to equate Moore's law with computation, but let's say it's computation capability. And this is data generation capability, which is sequencing. If your data generation capability greatly outweighs your computation capability, then you know that you have a problem, right? And it's going to become much worse into the future. Moore's law is because, as we discussed yesterday, is slowing. So our computation capability is not becoming better, at least at the fundamental device level, as much. But the technology scaling in genomic data production capability is becoming much better. As a result, the gap between computation capability and data generation capability is increasing and increasing. And we have a data bottleneck. Okay, so that I think clarifies it. Basically, we have sequencing machines that are very powerful, but the analyses that we need to make on what is produced by the sequencing machines to get to scientific discoveries, to get the medical recommendations, to get to discoveries in health and medicine, we're bottlenecked. And how do you solve that bottleneck? We're going to have more lectures on acceleration, basically. How do we accelerate genome analysis? This is very similar, in my opinion, to how do we accelerate machine learning? How do we accelerate databases? How do we accelerate any important application? I like genome analysis because I can show you clear trends over here, but you can also see clear trends with machine learning also. People have shown data is exploding in terms of how much data you need to train these models. And computation is, again, clearly not scaling very well as much as data. And memory is not scaling. Memory is scaling even worse, actually. But basically, acceleration is something that we're pursuing. And this also motivates, like last time we discussed, the hardware software co-designs, right? I'm not going to go over what we have done in the area, but we're going to talk more. But I think it's good to mention that whenever you see something like this, if your analysis is not efficient enough, you should really tackle it across the layers. And the first place to tackle is probably algorithmic and software. You should really check, are you doing any useless work in your algorithms? And that's what we did when we first started doing this. Basically, we looked at the genome sequence analysis systems of the day, software of the day. And we basically said, okay, this software is doing a lot of useless work because it's really not taking advantage of the structure of the genome, for example, to eliminate some useless computation. It's doing computation repeatedly many times. And if you eliminate that computation, then you can actually speed things up by orders of magnitude. In this paper, we show that you can speed up by 19x, for example, existing software. But that's not enough, of course. If you really want something that takes weeks and weeks to come to 1 minute or so, 19x is nothing. You need to speed it up much more. So later, we actually looked at SIMD units and accelerated genome analysis with that. We looked at FPGAs, and these are some papers. We looked at in-memory computing. I'm not going to go over the details of it since we will have more detailed lectures on genome analysis as a case study of how to do hardware software co-design and acceleration. And these all actually improve performance significantly, as well as energy efficiency. And we actually did algorithm architecture co-design. I think I missed something. Yeah, Shuji. This is one algorithm architecture co-design example that changes the algorithm and designs the FPGA according to the algorithm significantly. And this is a more recent work that comes up with even a different algorithm, basically. Basically, it has the insight that the read mapping problem, at least a portion of the read mapping problem, can be converted to the routing problem in VLSI. And it basically takes advantage of the algorithms that are employed in VLSI routing to do the read mapping much faster. And this is really the state of the art at this point. It actually appeared in late 2020. And this is really the state of the art in pre-alignment filtering, but we will talk about that later on. we also looked at, I mentioned yesterday, approximate string matching, which is at the core of many genomic analyses. Again, this is another hardware software co-design mechanism for that. And you will see more of this later on. And I think that in the future, we need to do more, basically, and we'll hopefully talk about that. I will just mention one thing over here. This is something that relatively simplified, but even nanopore sequencing folks, when they advertise their systems, they basically advertise by saying 7 hours RNA to answer. First of all, basically, they want to do the whole genome sequencing of the COVID-19, which is a good thing to say, a good thing to do, but this is the simplest of the analysis that you can do with COVID-19. But even there, even with such a simple task, the analysis taking 1 hour, which is quite long, I would say. Imagine now a human genome. Imagine you're examining, here they're examining only one genome, the COVID-19 genome. Imagine you're examining, let's say, thousands of genomes together and trying to compare them to each other, and also trying to compare the effect of different drugs or different variants or different vaccines, let's say, on the effectiveness of things. Then that analysis time will explode significantly. So I think this is very interesting to see. First of all, I don't know how this data is gathered. You need to trust nanopore technology for this, but there are more interesting analyses to do, clearly, and I'm not going to go over that. Then what I was talking about with thousands of genomes is metagenomic nanopore sequencing, for example, which they briefly mention over here. Okay. I will not talk more about the genome analysis portion, but I will refer you to these papers. You can read them early on. We're going to probably cover them more in a later lecture, and this could be an initiation to that lecture. These are past lectures that we have done in the last incarnation of this course, and we may actually, we will probably repeat some portion of them and also have more cutting-edge works described. Okay, let's see. Okay, let me finish the demanding workloads part, and then we're going to take a break. But basically, it's not just genome analysis, clearly. We discussed this yesterday. I think in general, I don't know why my computer is so slow. I thought I had a lot of memory in this, but yeah, in general, data is key for, basically computing is bottlenecked by data today, and data is key for many, many workloads. Machine learning is one example. We discussed it yesterday. Genomics, we discussed it today. Important workloads are becoming all data intensive, and data is increasing. We can generate more data than we can process. And even though these workloads require rapid and efficient processing of large amounts of data. So computing is not coping well, basically. There are other workloads that you can see. These are more traditional workloads, but the data that we throw at these workloads is increasing significantly. As a result, we have performance and energy bottlenecks. These are some other workloads on the mobile end. Again, data we throw at these workloads is increasing. And you can see the mobile machine learning frameworks as well over here. I didn't include the mobile genomics also. There's certainly mobile genomics over here. And as a result, data is really overwhelming modern machines. Basically, this is a paper we did with Google a few years ago, where we showed that more than 60% of the total system energy is spent on data movement alone, just moving data across the memory hierarchy between the main memory and the processor and across the cache hierarchy. So essentially, we have a problem at our hands. And the main reason for this is really the huge disparity between the energy and the latency of data movement versus computation. So if you look at this picture, a complicated floating point operation, arithmetic operation, is only 20 picojoules. These are values from 2015. These values have changed, but the trends are similar. Basically 20 picojoules, but the main memory, DRAM, read or write, is 16 nanojoules. That's 800x different, right? Okay, with what I know today, it's somewhere between 2 orders of magnitude and 3 orders of magnitude. Basically, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. 800x may be on the higher side today, but it's definitely closer to 200x, 300x potentially. So this is very interesting, clearly, to look at, right? If you are faced with a trade-off like this, then a good question to ask is, does it really make sense to bring data from memory to the processor chip to do a very simple, relatively very simple operation? Because we're causing a lot of energy to move the data. And the answer would be not necessarily. Later we will talk about in-memory or near-memory computation, especially if you do not have good locality in your workloads. You cannot exploit the caches extremely well. you cannot overcome this energy disparity between memory access and computation. And I haven't put the latencies over here, but latencies are also problematic, basically. This floating point operation is on the order of, let's say, 1 to 10 cycles. But this DRAM read or write is on the order of hundreds of cycles. So there's also a performance aspect of it, which we will see actually in the next lecture, hopefully. So we are faced with this sort of trade-off today. And I will also mention, this is really interesting. This is also an example of technology scaling, actually. If you took this picture, went back 70 years ago, let's say 1945 or 1950s, and tried to find the values that are associated with all of these operations, you would, it's not an easy task, but you will find that computation is much more expensive than memory at that time. Basically 2 to 3 orders of magnitude, maybe 2 orders of magnitude, okay. So what happened in the last 70 years or so is technology scaling. Logic has scaled really well. We really figured out how to reduce the size of a transistor, pack many of them, make them a lot more efficient. And as a result, the latency of the transistor, as well as the energy of the transistor, has become extremely small. But what we couldn't do very well with technology scaling is the interconnect and the memory cells. Basically, they did not scale as much. They scaled, but they didn't scale as much. As a result, the interconnects became the bottleneck, and the memory cell access became the bottleneck, which is also dominated by the interconnect, actually, usually. So technology scaling has brought us this new trade-off, basically, not new trade-off, but new disparity, let's say. Because we were so successful in improving the performance and energy of transistors, now we have a bottleneck in terms of memory and interconnect. And I think since we're talking about technology scaling in this lecture, it's good to have that perspective when you think about a picture like this. And again, all of these numbers, take those with a grain of salt. These numbers are very much dependent on the technology, depending on how you design some of the interconnects, etc. But the big takeaway, and people have published some recent numbers. In fact, there are some recent numbers that I will quote in later lectures that show that the number is today closer to 160 or 180 or something like that, as opposed to 800. But that doesn't matter. 2 orders of magnitude is still quite high in terms of the disparity, in terms of energy of these different operations. Okay, hopefully that's interesting. Any questions? Okay, maybe I'll finish these 2 slides. Okay, maybe I'll stop here now because this is longer than 2 slides. So if there are no questions, I would like to take a break at this point. Let me wait for a couple of minutes for questions. Anybody? Not a couple of minutes, probably seconds. Anybody on Zoom or YouTube? Okay, there's one question that I just saw on YouTube, I think. Is RowHammer only a problem for DRAM? Can RowHammer attack be generalized for various hardware components? So that's a very good question, actually. So disturbance in general, read disturbance in particular, is a very general problem. Basically, all memories have disturbance problems. So for example, flash memory, when we talk about flash memory, you will see that read disturbance is a huge effect. In fact, we were doing a lot of research on flash memory and finding a lot of read disturbance problems in flash memory. That's what's partially inspired us to look at essentially RowHammer also. So clearly, this effect exists in all memory technologies. In hard disks also, actually, read disturbance and write disturbance also exists in other memory technologies as well. It also exists in SRAM. Now, does it get exposed to software is the major question in RowHammer. And as far as I know, not yet. So flash memory has a lot of mechanisms to overcome the read disturbance. So it's very hard to exploit those read disturbance bit flips in flash memory. People have shown that this exists in emerging memory technology like STT, MRAM. I think there was an ICCD paper a few years ago that shows that there are RowHammer attacks on STT, MRAM, which is an emerging memory technology, which we will talk about later on. So fundamentally, RowHammer bit flips exist, but they may not be exploitable from the software perspective. Of course, if someone comes up with really clever ways of exploiting these bit flips somehow, exposing them to the software, then they become exploitable. So overall, I think what is interesting in DRAM is whatever bit flip you can induce directly gets exposed to the software. That's not the case, for example, if you correct those bit flips early on, right? Okay. Any other questions? Yes, please, in the room.
So what do you think determines whether, I guess a certain aspect can be improved exponentially or linearly? Because it seems like for the genomics side, for speed of computation, you're able to pretty easily, or I won't say easily, but you're able to improve it by like a crazy amount, like 10,000x or something, trying to bring it from weeks to like minutes. And yeah, like it seems like for energy, maybe it's a bit more difficult because you mentioned 63% of the energy is used for data movement. And that seems to be a large amount. And yet 63% improvement is nothing compared to a 10,000x improvement. So I guess, yeah, do you have any insights on what makes something exponentially improvable?
Yeah, that's a good question. I mean, that's not an easy question also, right? Because, I mean, it also depends on what baseline you start with, right? If your software is really poorly done, getting to 10,000x may not be that hard, right? I think, but it's usually the remaining, let's say 100x that's really difficult in the end, even in performance. But yes, if you look at energy, for example, yeah, I mean, I don't have a great answer to your question. I think it really depends on the case, depends on what baseline you start with, and also what techniques you employ, right? So 63% is just data movement, by the way. It's not, it doesn't include, for example, refresh, storage, so there's more energy that's wasted. But yes, just by tackling the data moments, I think you cannot get extremely high benefits. You really need to do something else in addition to that. Does that make sense? Like you may want to improve the energy efficiency of other parts of also, right, of your interconnect. You may want to get rid of the refresh power, etc. So it's really multidimensional. So when I talk about and also that 62%, I should also say, okay, I think you bring up a very good point. The 62% number is averaged across multiple applications. So it's not application specific. So when I look at the genomic analysis number, we're focusing on one application and a specific part of genome analysis. So if you focus on one application and co-design hardware and software, you can achieve much higher benefits. Maybe maybe the comparison between 10,000x and 63% is not fair from that perspective. Does that make sense? So I think the appropriate comparison perhaps could be, okay, I'll take the genomic application and improve its energy efficiency. What is it that I can achieve, right? I believe you can still get to orders of magnitude that way, because the improvements that we do in performance actually improve the energy efficiency also. So the 63% number was really average and across different applications, not genomic applications.
Yeah, I think that makes sense. Like, I guess like it's because like if you look at the hierarchy you presented, the genomic one's at a much higher level, and so you have access to a lot more flexibility in the design solution. And so in reality, it actually contains the energy improvements. So the 10,000x improvement in the performance of genomic analysis actually means in that specific application a 10,000x improvement in the energy efficiency as well, probably.
Yeah. I mean, we didn't measure energy efficiency in all of our improvements, but I believe to a first order that is correct. Basically, performance improvement translates to energy because you're eliminating useless work. But exact numbers we didn't measure. Okay, these are very good questions, and I like the fact that people are interacting over multiple modalities, let's say. Okay, there's, I think, yeah, there's one question on YouTube. How do you compute power during data movements? Well, it's really the amount of power you spend, the amount of energy you spend, right, due to data moments. Like every data moment, you can see that there's some energy you spend for DRAM access, 16 nanojoules, and you can multiply it by time if you want to compute the power, or integrate it over time if you want to compute the power of it. I think that hopefully answers the question. Okay, I think this is a good time to take a good break. Let's be back after 16 minutes. It's 2:50. And then we will continue with the trends, and hopefully we will be able to cover some course logistics as well. Okay, see you soon in 16 minutes. Okay, I think it can. I think we can get started. Can people hear me? Let me see. Okay, I think I can see people also. That's good. I'm not sure if you can hear me though. Can you? Hello? Okay, I see one hand, one thumb up. That's good. At least one person hears me. That's good. On Zoom, yes, that's good. Okay. Okay, let's continue where we left off. We were talking about the interesting things that are happening today in computer architecture. I think I can go on, but I think I'll summarize at this point so that we can go more in depth in later lectures. Essentially today, because of the trends that we have partially looked at, important trends that we have looked at, and the requirements of the applications, the demands of the applications, there are many new concepts are investigated today. I think the trends, I mean, we have talked about demanding applications. We have talked about technology scaling issues. And we also talk about the demands of the users, right? More energy efficient computing, higher performance, more reliable, safe, secure, private computing devices. Basically, to enable all of those, to cater for all of those, today people are really investigating many novel concepts, both in research, as well as some of these research ideas that used to be research ideas are actually now going into products. For example, we're looking into new computing paradigms, which enable us to rethink the full stack. Processing in memory, near data processing are examples of it that we discussed. There's also neuromorphic computation, which has similarities with processing in memory, but they're a more specialized form of processing in memory in the sense that you're looking at more spiking neural networks and try to imitate them in hardware. That's also interesting, certainly. And people are trying to design, or at least in research, they're trying to work on fundamentally secure, dependable, and robust computers. And industry is hopefully going to get to that point as well, with more demonstrations of these security problems and how important they are. The second part is new accelerators. People are clearly, this is happening a lot, right? Algorithm hardware co-designs, I would say. And I showed you a lot of examples of machine learning accelerators. We talked about genome analysis accelerators. There's graph analytics accelerators. And you can think of other workloads. And we had a discussion of that yesterday as well. And people are also looking into new memories and storage systems, as we talked about non-volatile main memory and more intelligent memory systems in general, putting more intelligence into the memory side. Probably I can expand this slide more, but I want to keep it this way. We're going to talk about a lot of these issues and more going forward. But I will emphasize that the applications will continue to push forward, basically. Humans are somehow, let's say, greedy in terms of what they want to achieve and what they want to solve. And essentially problems keep increasing as opposed to stopping. We do in all aspects of life. As a result, I think we can be sure that there will be more and more intensive applications going into the future. Hopefully useful ones, I should say. As we mentioned yesterday, technology is agnostic to ethics, right? You can come up with good applications or bad applications. Hopefully it'll be good for the humanity, of course. And the key trend is that we have increasingly diverging and complex trade-offs, as we discussed a few minutes ago before the break. Essentially, this is one example of that, right? A memory access consumes 2 to 3 orders of magnitude the energy of a complex addition, and that's a problem. And that's one example trade-off. There's performance trade-offs also that we didn't cover over here, but we will talk about when we get to specific points. And systems are becoming increasingly complex as a result of the need to cater to technology scaling issues, as well as application requirements, as well as energy efficiency, performance, drive, let's say. Past systems used to look like this. In fact, if you looked at a CPU, it wasn't even multi-core, right? It was a single core processor. It didn't have even extensions like SIMD extensions, like I mentioned yesterday. It was a simple pipeline, let's say, executing a simple, I don't want to say simple ISA, but a single ISA. And that doesn't have a lot of acceleration capability inside the chip, and some simple memory and simple storage. Now, I should have updated this picture with some of the more recent CPUs, GPUs, and FPGAs. Maybe I'll do that in a later lecture. But today's systems are much more complicated in all aspects, basically. you have memories that are complicated, meaning there are multiple types of memories. There are multiple types of persistent memories, SSDs, hard drives, etc. You have, even within the CPU chip, the main CPU chip, let's say, you have a lot of different accelerators today. You have vision accelerators, you have machine learning accelerators, you have different types of cores, not just a single core, but not just multiple cores, but different types of cores, heterogeneous cores as well. Some of them are optimized for power, they're simple, and they're many. Some of them are optimized for performance, they're larger and they're fewer. Like if you look at the recent Apple M1 chip, which I used to show in my digital design course, but I will also probably show it in a later lecture over here. It consists of many, many accelerators internally. There's also a GPU integrated into the main processor chip. So even if you look at a processor chip internally, it's a highly integrated, heterogeneous system internally, right? This is also enabled by technology scaling and Moore's law, right? Because you can have many, many transistors that can be put on the chip. So this integration capability has increased significantly. But on top of that, we have separately FPGAs and maybe more powerful GPUs that you cannot fit on a single chip that is shared with processor and other components that are also accessing the main memory. So we have heterogeneity at the chip scale, and we have heterogeneity across chips as well. And that's also happening inside the memory as well. You have heterogeneity across the memory hierarchy, and you have different types of memory. Even within the main memory, you may have a high bandwidth memory supplemented by a regular DRAM main memory that's not optimized for high bandwidth, for example. That's heterogeneous main memory for you, and that has been increasing more recently. GPUs are an example of this, but there are other systems like Intel's, I think Knight's Landing, they used to call it, had a high bandwidth DRAM as well as a regular DRAM too. Okay, so basically there's no question that systems are becoming increasingly complex, both within each chip as well as across the diversity of the chips. And of course, managing this is becoming even more important. And as a result, computing landscape today is very different from 10 to 20 years ago, even 5 years ago, I would say, actually. 5 years ago, we didn't really have this explosion of accelerators. And applications and technology both demand new architectures. And as I mentioned in the last lecture, every component and its interfaces, as well as entire system designs, are being re-examined today. And as a result, things are becoming more complicated, hopefully better, but not necessarily better, right? If you have too many interfaces and the interfaces are what's limiting you, then you have a problem also. And as we discussed yesterday, some of the interfaces are limiting us significantly, like the hardware-software interface today. The way it's designed, you cannot communicate a lot of semantic information from the software to the hardware, as well as backwards. Okay, but I think this is still a very good time to study computer architecture because, in my opinion, if you understand the entire stack, architecture at the center, hardware and the software, as well as go down to devices and go up to algorithms, then you can actually really revolutionize the way computers are built today. And that's, in a sense, that's happening across the industry, right? People are really trying to change the entire hardware software stack so that they can put in a tensor processing unit, for example, right? That's one example. The Cerebras example, so that they can put in this wafer scale chip. They need to change the entire stack so that they can be much more efficient, let's say. But I think these are good examples. Processing in memory, of course, another example, right? If you have processing in memory, you're really changing the computing paradigm now. But you can invent new paradigms for computation and communication and storage, and this is a very good time for thinking about it. And if you're interested in this sort of analysis of how science and engineering improves with revolutions, I would recommend a book that was written by Thomas Kuhn, who's essentially a philosopher of science. He really analyzes how science has evolved, and he tries to see patterns in the development. And he wrote this very interesting book in the 1960s, where he said that science and engineering, I also take the liberty to extend this to engineering, but he says that science evolves and revolves, let's say, in multiple ways. At some point, there are no, basically, usually, you're in the normal science domain, meaning there's some dominant theory that's used to explain and improve things. Exceptions are considered anomalies, right? So, okay, let's go back to Middle Ages. And the theory I don't know if it's scientific or not, but people used to explain that the sun revolves around the earth, right? And some people come up with exceptions that say, oh, okay, sun is not really revolving around the earth because of these reasons. Those are anomalies. But after some point, there are so many exceptions that people say, okay, we really need to rethink the existing theory. And then that theory gets overhauled, if you will. That's called revolutionary science. And there's so many exceptions that the theory cannot really satisfy you anymore. So you need to come up with a new theory, or a competing theory succeeds. So the earth revolves around the sun, right? In the meantime, many people may die because people may not want to change the status quo, right? If you read the book, you will see that effect also, right? Because you're really changing something important, and some people may not want that change overall. So that's revolutionary science. And after that, of course, there may not be some clear consensus in the field. There might be some pre-paradigm science. Maybe there are multiple competing theories that try to explain the situation. And at some point, one theory wins, or maybe multiple theories are thought as explaining a phenomenon, right? But after some point, normal science continues. Maybe you have dominant theory or multiple dominant theories. So I picked Earth revolving around the sun versus sun revolving around the Earth as an example, as an extreme example. That's also covered in this book, actually. There are many other examples covered in the book from physics, chemistry, etc., astronomy, etc. I'm not going to talk about that. But I think computing can be applied to this framework also. So in like 20 years ago, let's say, the dominant theory, let's say dominant practice, I will say in this case, was to actually design single core processors, heavily pipelined or reasonably heavily pipelined, increase the frequencies, increase the pipelining level, and you have a general purpose processor, superscalar, out of order processor with heavy branch prediction, etc., heavy caching, and that's considered the best way of designing computers. Now that doesn't exist today. People have poked so many holes, so many exceptions against that practice, and they have shown that, okay, this is not energy efficient, this is not high performance enough, this is not secure, etc. So it was really attacked in all dimensions with many, many exceptions, showing that this sort of design is not good. It cannot be, let's say, good for solving many problems. And as a result, I think we're still in the midst of a revolution. We're still figuring out what are the best ways of designing computing systems of the future. That's why we're seeing more specialization in terms of accelerators, right? People clearly have tackled the general purpose. General purpose has some domain, of course, but it cannot really be efficient in all cases, right? So I think today we're in this revolutionary science where we're really examining underlying assumptions of everything in computing, especially the computer architecture and hardware, and also how the software is designed on that hardware. So in my opinion, there is no clear consensus in the field, but there's some high-level consensus emerging, which I have been advocating for some time. I think I see other people also advocating it more and more these days, which is really what I mentioned earlier, right? Yesterday, it's really this across-stack design, hardware, software, co-design, and that I suggested as the axiom, and that really leads to the highest energy efficiency and performance. So you need to really co-design across the layers and optimize. But there's a lot more to do, I think. There are many, many other paradigms to look into today. And this is Thomas Kuhn, by the way. And if you're really interested in learning more about his book, he has books. This is the book basically that I mentioned. It's actually a beautiful book. It's not an easy read, but I think once you get the hang of it, it's a beautifully written book. Okay, so let me conclude this part. I think it's really an exciting time today to be understanding and designing computing architectures for all the reasons that I mentioned. We really have a lot of problems at the applications, algorithms, problems layer. We really have a lot of problems at the technology and circuit layers. And we really have a lot of opportunities at the technology and circuit layers going into the future. And we really have a lot of opportunities at the top also. The key is really how do we design entire systems such that we solve the problems at both layers and also merge the layers across, let's say. So there are certainly many challenging, exciting problems in platform design to enable this, and that no one has really tackled or even thought about before. So RowHammer, if you think about it, it's a very relatively new phenomenon, right? Processing in memory is not an old phenomenon, old idea, but you need to rethink it carefully and completely to enable it today. And there are many other examples. I mean, GPUs are relatively new also, if you think about it, in the history of computing. And maybe there are some other execution paradigms that are going to be important. Okay, and that can also have a huge impact on the world's future. AI accelerators, machine learning accelerators, also clearly new. They're no older than 5 years or 6 years today. And I mean, as I mentioned earlier, this is really driven by applications at the higher end of the stack. We can easily collect more data than we can analyze and understand, and we can easily dream about new applications today. And it's also driven by the bottom parts, which is significant difficulties in keeping up with the hunger at the technology layer. Basically, a lot of technology scaling issues. And all of these together lead to energy, reliability, complexity, security, and scalability problems. And you can certainly add safety and dependability, etc. over here, or more robustness, the term robustness in general. So we have a lot of interesting problems to solve, basically. And again, I will also mention that we have problems at the top and the bottom. But again, I think we have a lot of opportunity at the top and the bottom of the computing stack also. Okay, with that said, I think let's start with some fundamentals. Again, I'm going to keep it at an idea level at this point. We're not going to, we're actually going to have some fun at this point with real architectures, not computer architectures. But I think this design mindset, the principal design mindset is important. Any questions so far? Okay, I think I don't see any questions. I think on YouTube, Ataberk mentioned that Ataberk gave the paper that I was mentioning, which is analysis of RowHammer attack on STT RAM. And so that's the paper I was mentioning. Thanks, Ataberk, for providing that. Okay, so let's start with some fundamentals. I think what I would like to do in the remaining part is to hopefully instill you with the principal design choices and what I mean by that. Maybe I'll ask this question. Does anybody know what this is? If you've taken digital design and computer architecture, maybe you don't need to say. Anybody? Okay, go ahead.
Isn't that the train station in Stadelhofen?
Yes, absolutely. Yeah. If you're using it, probably it's hard not to recognize it. Yeah, this is the train station at Stadelhofen, Bahnhof Stadelhofen, basically. And that's one answer to this question. Anybody else wants to venture another answer? Because any question can have multiple answers also. And that's one of the lessons that I would like to do have over here. Go ahead, please. I see a hand. Yeah. I couldn't hear you. I heard it's only.
Bottleneck. It's a bottleneck.
Okay, so I didn't think about that as that, but yes, I think that's probably a good answer also. So how did you experience that as a bottleneck?
Well, the train station only has 3 tracks and all the other ones on the line have 4. So whenever there's a problem with the train being delayed, the train station is where the problem manifests itself. Okay, that's excellent. So I need more pictures to really verify that. But yes, I think I agree with that. And that's a very fundamental principle also, right? Whenever you reduce the bandwidth, then you create a bottleneck, right? In fact, it's also recognized by Mike Flynn in his seminal paper in 1966, Very High-Speed Computing Systems, where he talks about balanced design, right? I think this design is not balanced globally, let's say, because around it, maybe you have 4 tracks and then it reduces to 2 tracks. I haven't thought about it that way, but I think that's a very good answer, actually. Very relevant to what we're going to study as well. Any other answers? So it's good, I think, because now I think you're thinking with the mindset that I would like people to think, which is, or I would like to encourage people to think and consider thinking about, which is really how you think about systems in general, right? When you look at a system, this is a system, and what does it affect in terms of interaction with the users, as well as in terms of interaction with other components of a bigger system. And I like the bottleneck answer. Okay. But my answer to this is the first piece of a major, this is the first major piece of a famous architect. Basically, it actually carries the signatures of the work of this architect, which means examples are straight lines and right angles are rare. And we're going to see more examples of this. Does anybody know who this architect is? Yeah, go ahead, please.
Santiago Calatrava.
Yes, that's correct. I think somebody on Zoom also answered it correctly, so that's good. Have you taken digital design and computer architecture? No, okay, good. That's even better. Yeah, because I covered something similar in digital design and computer architecture, because I think this is very fundamental in the end. Okay, yes, so the architect is actually an ETH alumnus. He has a PhD in civil engineering, but he's a very multifaceted person, not an engineer only, but also an architect. And it's Santiago Calatrava. Okay, if you compare that station to this station, you can see that this could be a bottleneck also, right? I guess I didn't look at it from that perspective in the past, but this also has the resemblance of a bottleneck, at least the way I look at it over here. But that's not the aspect with which I was going to compare the two stations. I think this is an okay station. I'm looking at the more structural aspects of it, like the design, right? This station is more, let's say, traditional and conventional, right? And I would say that the previous one, so they're different. Let me say that there are different principles employed in the design of these two stations. This principle is optimizing for some metrics, and maybe these principles are optimizing for some other metrics, right? And we will talk about that. Again, I don't want to really go into details of those metrics other than giving you the examples that these are actually designed for different metrics in mind, including what the architect wanted to do, of course. Okay, I would argue that the station over here, from my perspective, is much nicer to be in, if you will. Although I could see that somebody else arguing that this is much nicer to be in as well, right? Okay, so another question, what is this? Yes, please, another hand.
An example of branch prediction. No, not this one. The thing just before.
Wait, which one's the branch prediction?
Go back to the train station.
Okay.
This is branch prediction, right?
Oh, because of the tracks going.
Yes.
Okay, I see. Yeah, that's another way of looking at it, sure. You have to pick one route, right? But if you mispredict, you have to go back then. Yeah, this is a tough, it's a branch misprediction with a high misprediction penalty, perhaps. Okay, cool. Yeah, I like the way you guys are thinking about it. Okay, I was thinking more structural aspects. Okay, what about this one? Does anybody know what this is? No one? Yes? Yeah, maybe the person on the right of the room, or left. There are two competing people, so whoever reaches the microphone first.
Well, it just says at the bottom, this is another building by Santiago Calatrava.
Oh, yeah. Okay, but which one? I guess you read it, Oculus World Trade Center. But you're exploiting side channel information here. But yes, this is the Oculus, which is Santiago Calatrava's, let's say, the masterpiece at this point, or at least one of his masterpieces. And clearly, this is based on similar design principles, actually, to this one. And we'll talk about that. I think my point is really principal designs over here. So Calatrava designed this to resemble a bird being released from a child's hand. So it's really based on the designs. And there was actually more thought in the design, like the roof was originally designed to mechanically open to increase light and ventilation to the enclosed space, etc. But it didn't work out that way because of cost constraints, as we will see. Actually, this is a building that I visited many times, and people who visit this building send me pictures of it, and it's after taking my class, of course, and it's a lot of fun. It's in New York. Okay, so why am I talking about this? I think, first of all, there are principal designs, and I'm going to show you more examples of it. But also, these designs have trade-offs as well, both upsides and downsides. And trade-offs depend on the metrics you evaluate them with. Okay, so this is basically reported by someone. You can keep reading it, of course. But this person says, it's a pleasure to report for once that public officials are not overstating the case when they describe a design as breathtaking. So clearly this person is evaluating this Oculus design with some metric, right? And that could be maybe the happiness level you feel when you're inside the building, right? I don't know. But clearly, if you take another metric, it looks different, perhaps, right? So here, let's take a look at some design constraints that caused this particular Oculus building to be less than what it was intended to do. For example, Calatrava had an original design with a soaring spikes, but it was scaled back due to security issues. Now you're seeing real issues, real design constraints, and criticism comes after that. As you can see, somebody wrote, in the name of security, Santiago Calatrava's bird has grown a beak. Its ribs have doubled in number and its wings have lost their interstices of glass. The main transit hall, this is supposed to be a train station actually, between Church and Greenwich Streets, will almost certainly lose some of its delicate quality while gaining structural expressiveness. It may now evoke a slender stegosaurus more than it does a bird. And if you don't know what a stegosaurus is, it looks like this. And there is some resemblance, perhaps, yeah. Okay, so I think the point is design constraints are real in anything you design, and no one is immune to them. And security is a critical constraint, as you can see. And that's true for computing systems today, but that's also true for other systems like that have interactions with humans, that have effects on humans. Clearly, security is a big issue in building design, and Calatrava was not allowed to do what he wanted to do. And then there are other constraints, not just security. Cost and space area are real constraints also. The design was further modified in 2008 to eliminate the opening and closing roof mechanism because of budget and space constraints. Again, this is very real. In computer architecture, you will face that all the time. However much budget people may think they have, they will always be limited by cost. And my favorite example here is supercomputers, for example. Usually, these very high performance computing systems, supercomputers, people try to build them to maximize the performance on a handful of applications, right? And energy efficiency these days. These days, actually, supercomputers are evaluated not just on performance, but also energy efficiency, because they are really related to each other. But it's really for a handful of applications that people deem important for supercomputers. And usually the thinking is that these systems are bought by governments who have a lot of money, deep pockets, regardless of however they obtain it. That's not what we're involved in over here. But and as a result, they're not cost constrained. But that's not true. These systems are also cost constrained. Even the most costly systems that people think can be afforded are cost constrained. So if someone says cost is not an issue, it's just a matter of limit. Right? At some point, you have a limit. Okay, and you can see that in this particular case, the transportation hub, which is the Oculus, has been dubbed the world's most expensive transportation hub for its massive cost for reconstruction, $3.74 billion. That came from, I guess, New York, people of New York. ... So some people were quite not happy about it, clearly, pouring so much money into this. But I think I will also mention, let me see if I can go into, okay, before, this is also a paradigm change. In a sense, if you apply this analogy to computing systems, maybe you think about a transportation hub, a train station, as we saw earlier. You have a conventional paradigm that's not costly, and you change the paradigm completely. It becomes something like a masterpiece, let's say, but it costs. It comes at a cost. So basically, there's no progress without cost, I will say. If you really want to change a paradigm, like what Calatrava is doing over here, in my opinion, then you have to bear the cost of it. And I think that's true for progress in computing systems as well. You want to change the paradigm from processor-centric to data-centric? Yes, it comes at a cost. You need to change the manufacturing capability so that you can manufacture logic inside DRAM, for example, or you can make robust computation inside DRAM. And you need to change the system software stack and the hardware stack so that you can actually take advantage of this data-centric processing in memory paradigm. In that sense, I think there are a lot of similarities. There's no progress without cost, I will say. But once you, another example is a phase change memory that we discussed last time, right? If you want to get phase change memory and enable it, you need to invest a lot of cost into it. It's completely different from a volatile memory because the manufacturing processes are completely different, etc. And in the end, you will hopefully have a much better system. There will be criticism of it, just like there are criticism of Oculus. People will say, oh, why do we need persistent memory? Why do we need one non-volatile memory? My application doesn't require it, etc. You will see all sorts of criticism like this. There are security issues also, clearly. If your data stays non-volatile, and if it doesn't go away, then someone can actually potentially inspect that data, right? Or it could lead to reliability issues. But basically, it can be criticized, but it comes at a cost also, because you need to provide the manufacturing capability, you need to provide the system design, you need to provide the architectural changes, you need to provide the software stack changes to support that new idea, let's say new paradigm. So that's why we're having this lecture like this right now. I think the fundamentals are very similar in all system designs. There are trade-offs and there are metrics, and if you really want to make progress and change the paradigm, you have to bear the cost. I think the good thing is once you bear the cost and once you actually make the decision to move to a new paradigm or complete a new system design, then you can reap the benefits of it. And over time, the cost may be amortized. Of course, you don't know that before you make that decision, right? Before you make that decision, it feels like the cost is huge. And over time, if things get used, then the cost is amortized. And I think the way I look at Oculus is, yes, maybe $4 billion is a lot. Maybe it's a bit extravagant, but now people go over there and this place is full of people and they really enjoy it. So maybe they amortize the cost over time, right? That's not a great argument, of course, in a financial perspective, but you see, hopefully you get, you see what I'm getting at. I think cost of, for example, a new paradigm like processing in memory or non-volatile memory can be amortized over time by reducing the cost of energy we spend on data movement, for example, reducing the cost of energy we spend on manipulating persistent data, and reducing the performance cost also, right? Making our systems a lot more efficient. So I think it's good to keep this in mind. Yes, new ideas come at a cost, but that cost can be amortized because new ideas lead you to a point that you were not before. And as a result, that point can be a lot more efficient than the previous point you were at. As a result, hopefully, if you remain at that point long enough, you can amortize the cost. And I think this is true for, in general, the new technologies as well. If you, for example, move from CMOS to carbon nanotubes, yes, there's a huge cost to make the jump from CMOS technology to carbon nanotubes. But if you stay at carbon nanotubes and if it's really efficient, then you amortize the cost over the time you use that technology. Another example we discussed yesterday, the multimedia extensions in Intel processors, right? Actually, this was a huge cause of controversy inside Intel in the 1990s. People were saying, we really need these extensions. We need to pay the cost, get them out there. People will use it. Multimedia applications will run much more efficiently in our systems. Other people were saying, this is a lot of cost. Nobody's going to use it. How do we know people are going to use it? At some point, you need to really shift the paradigm. In this case, it's a maybe smaller paradigm shift, but from the cost perspective, within Intel, people were divided basically. And let's say cost benefit perspective. But clearly they made the choice to go with it. And clearly we see the impact of it, right? Those multimedia extensions have been extremely powerful and extremely useful, and they've evolved over the years. And clearly in hindsight, we can see that, oh, that was a good shift, right? I think there's no question about the fact that the multimedia extensions were a good shift today. It did add cost and complexity to the system, but it did enable a lot of applications like multimedia applications to be much more efficient. And we are also using it for genomics, for example, today, but other people are also using it for other things. Okay, I spent a lot of time on this particular slide and the analogies with architecture, but I think it's really important to keep these things in mind. And a lot of technology, a lot of ideas we will cover in this course are going to increase the cost in some way. But whenever you're challenged with this argument that, oh, but that increases the cost, you should always also consider the benefit that comes with it. And the benefit is not just immediate benefit. The benefit is also just a long-term benefit. If you can jump to a point where you're 100x more efficient in terms of data movement over the course of maybe 5 years after you move to a new paradigm, you can amortize the overall cost perhaps, right? And also cost reduces over time, I should say that. So initially, by moving to a new paradigm, your cost is very high. Going from, let's say, DRAM to phase change memory. Your cost is extremely high because DRAM process has been, manufacturing process has been optimized for decades and decades and decades and decades, right? Phase change memory, it's a new technology, at least from the DRAM perspective, at least from the main memory perspective, it's a new technology. And people need to develop the manufacturing process from scratch to enable it. So initially cost is very high, but over time you optimize the manufacturing process. As a result, the cost of that also goes down, right? So cost is a very dangerous thing to think about. Well, you need to think about it, no question about that, but it's also easy to make, let's say, wrong decisions with, because you need to consider not just the immediate cost, but you need to but also the long-term cost and how the cost will evolve over time. Okay, so hopefully this is clear. Any questions? Okay, yeah, feel free to ask questions as I go along also. So I think maybe I'll ask another question here. Does anybody know what this is? Maybe this is a tougher one. Yeah, maybe digital design and computer architecture students would know. Okay, a picture that I have seen at high school in my art class. Really? Okay, that's good. But you don't know what it is. I guess that's one description of it. But where is this picture at? Okay, Pittsburgh. Close, not exactly Pittsburgh. So this is actually the building that I developed this concept of using architecture to motivate decisions in computing systems. It's Falling Water. It's close to Pittsburgh, where I used to teach Carnegie Mellon University. My answer is, again, it's the masterpiece of another famous architect, actually. And in this case, the famous architect happens to be whom? Well, I guess I've already given you the answer. Frank Lloyd Wright, who was perhaps the most influential American architect of the century. And this is actually a building that is taught in architecture classes as a really masterpiece. And if you get a chance, I would recommend visiting it. And you can see that it has it has received a lot of accolades, if you will. But I have a similar thing over here I will talk about related to it. Basically, it's also a principled design. And it also came at a cost. This person did not build. Oh, okay, I think somehow I missed this picture because of my Zoom or PowerPoint. I don't know what's going on with my computer. But this is another picture of it. This person did not build a regular house. He built a house on top of a waterfall. And you can see that this is an example of the principle of organic architecture he used to employ. And you can see that the house is constructed to imitate the waterfall. So you can see that these cantilevers are really imitating this part of the waterfall and this part of the waterfall in a sense. And there are other features that you do not see over here that is really imitating the environment that this house is really constructed in. So it's really principled design, but it came at a cost also. And maybe we'll talk about it when we get to later slides. Basically, the people who commissioned the design had to tell Frank Lloyd Wright, stop, we're not paying you any more money. And these people were quite, let's say, wealthy people. Okay, so I would encourage you to go and visit Bahnhof Stadelhofen since it's close, and extra credit, repeat for Oculus. There's no real credit for it, but I'm happy to receive pictures from these different places. And you can repeat for Falling Water also. And I think you can hopefully appreciate the beauty and out of the box and creative thinking of these places. Well, if you haven't appreciated Stadelhofen the way I'm portraying it, maybe you will appreciate it now. And I would think about the trade-offs in the design of the Bahnhof and also these other buildings, their strengths, weaknesses, goals of design. And okay, I don't know what's going on with my computer. And you can also go further and derive principles on your own for good design innovation, right? Of course, any time during this course is better, but once you get into this trade-off analysis later during the course is even better. And hopefully you can apply what you learned in this course as a systemic way of thinking about trade-offs in design in general, and not just in computer architecture. I strongly believe that the principles that we employ in the course, I'm certainly critical thinking, but also the trade-off analysis is applicable in general to every problem you face. And I think that's the principle of engineering in general, but computer architecture happens to be at the heart of it. Okay, let's take a look at this. I'm going to go through this relatively quickly because I think after all we discussed, what I'm trying to do is hopefully obvious. So this is this. So we'd like to find the differences between this and that. And this is Bahnhof-Stadelhofen, and this is the unnamed Bahnhof over here. Some person in my course found out that this is some Bahnhof in Germany, I think. I don't remember where it was exactly. You can probably find it by clicking on this link that I have over here. But clearly there are differences in the design over here, right? They're optimized for different things. And I think creativity plays a big role in this first one, whereas it plays a smaller role over here. This is designed for regular use, and there's some artistic perspective over here that's included that doesn't exist in the second one. So you can certainly list them over here. But I think this brings me to evaluation criteria for the designs. We've been talking about some of these things over the course of the last meetings, let's say. But clearly, there are many evaluation criteria for the designs. This is true for architecture. This is true for computing systems. Functionality is an important one. Does it meet the specification? Reliability, robustness, space requirement, cost, expandability, comfort level of users, happiness level of users, aesthetics, etc. You can come up with many things over here. Security I don't include over here, but that's certainly an aspect as well. So how to evaluate goodness of design is always a critical question. And this evaluation criteria is really what distinguishes the trade-offs of different designs, basically. A design may be great in terms of, for example, cost, the unknown or unnamed station in Germany, but it may not be great at aesthetics, right? I understand that aesthetics is in the eye of the beholder, but I will argue personally that Stadelhofen is aesthetically more pleasing compared to that unnamed Bahnhof. So basically, it's really all about juggling the trade-offs for different metrics, and it's all about your design criteria in the end. You come up with a design criteria and you design for it. And normally, ideally, what should happen is you want to optimize for multiple design criteria that you choose. This doesn't mean that you should ignore other design criteria because they may actually come back and hurt you in the end, right? For example, you can say, I only want performance, and then you don't even consider security. Then 20 years later, somebody comes and says, because of the decisions you employ to maximize performance, I have side channels in your processor, right? I only want capacity in my DRAM chip. I don't care about reliability as much. And 5 years, 6 years later, someone comes and says, oh, you have bit flips in your DRAM chip, and you have a reliability and security problem. So that's why I think it's good to be comprehensive when you're designing systems and consider different metrics and never leave a metric completely unattended, let's say. And this is especially true today when technology scaling, we're really pushing forward with technology scaling to the edge, let's say, because that is really affecting all of the reliability and security issues that we discussed. Okay, so another key question is, how was Calatrava able to design his key buildings? I'm now looking at it from the perspective of how do you become a good architect, let's say, right? And I think there are many guesses we can have, of course. And I think a big combination of it exists in Calatrava: hard work, perseverance, dedication over decades, experience, creativity, out-of-the-box thinking. He probably had a good understanding of past designs, because if you have a good understanding of past designs, you can do better. Good judgment and intuition, strong skill combination, math, architecture, art, engineering. Funding is important in a project like that. Luck, initiative, entrepreneurialism, and strong understanding and commitment to fundamentals and principled designs, I would say. And who knows what else, right? You can probably add more to it. But I think these are, of course, in hindsight, the way I explain how this architect may have constructed his key buildings, right? And I think in general, it's a combination. And I think computer architecture is kind of similar, right? If you want to do a full system design, new computer architecture, or a new idea, enable a new idea in computer architecture, you really need to have a combination of a lot of these. Some of them may be more important or less important, depending on the idea, depending on the design. But I think a lot of these are important. And hopefully this course will give you the intuition to develop some of them and maybe have some of them relatively quickly. I cannot promise funding though. That's not something I control. But yeah, that's what I say over here. But I think most importantly, perhaps these two are things that we will emphasize, like principal designs. What is the principle in a design? For example, data-centric computation versus processor-centric computation. I think these are complete different principles. They employ different principles, and also fundamentals of the fundamentals of design. And we're going to cover that a lot with every single idea that we examine in this course. We will talk about, of course, metrics, but that was a previous that was a previous slide, and that was a different question. Okay, so what is principal design? Essentially, I mean, I will give an example from Calatrava over here. He says to me, there are two overriding principles to be found in nature that are most appropriate for building. One is the optimal use of material, and he goes on and describes what that is. The other, the capacity of organisms to change shape, to grow, and to move. And other people also confirm this. Basically, Calatrava's constructions are inspired by natural forms like plants, bird wings, and the human body. I don't know about the optimal use of material. I think that's his perspective on how nature works, I guess. I'm not sure if it's proven, but again, this is a principle, right? You can develop a principle based on axioms. They don't necessarily need to be proven in this particular case. So you can see in his design, actually, this is Gare do Oriente in Lisbon, another train station. He's famous for a lot of his train stations, you can see. And that's, again, inspired by humanoid forms. And his principles are usually, can be usually described as zoomorphic architecture, which I'm not going to go into the details of. But other people also employ this principle to design buildings. What does this remind you of? Does anybody want to take a guess? I guess we kind of discussed this, right? It's a bird or a dinosaur or whatever right now. It was intended to be a bird, but apparently he said in an interview that it was a bird coming out of a child's hand, right? I don't know if it resembles that. But again, these are principal designs. What about this one? This is in Sevilla, Spain. Anybody from Sevilla, Spain, or anybody knows this? What this looks like? Some people say harp, but I'm not sure that was the intention. This looks like a pigeon, right? There's an eye over here and a mouth, and the pigeon is looking backward, maybe like this. Anyway, that could be the intent over here. Okay, I think I can go on and on over here, but maybe I missed some of these. Okay, this is Sevilla. This is Milwaukee Art Museum. This is Athens. This is Valencia. It's a beautiful building. I've been to several of these buildings, not all of them. I'm looking forward to going to more. This is an interesting one. Here, he had the money to actually do it. It's really opening up, as you can see, like a bird. This was the intent with Oculus, but apparently this university had a lot of money to waste. But the New Yorkers didn't want to waste their money on that. So you should also think about it from that perspective, clearly. I wish universities spent more money on actual research and education than building buildings. But somehow donors are more interested in seeing immediate things that are put on ground as opposed to long-term consequences of good education and research, which is clearly not easily measurable, right? You're looking at 20 years down the road. In the latter case, you're looking at 1 year down the road when you construct a building. Okay, so yeah, that's my comment. Critical comment, let's say. Okay, so this is the other famous architect, Lloyd Wright. He actually poses this very clearly, I think. Architecture should be based upon principle, not upon precedent. So I like this, actually. This is very nice because if you want progress in a field, you should not really imitate what came before, right? Precedent is what came before. If you really want to have progress, you need to base your progress on principles, solving the problems fundamentally, as opposed to doing business as usual. That's what he's getting at over here, basically. And I like this mentality. And as a result, Frank Lloyd Wright did not build this building. So if you look at this building, it's a regular building. You can find this a lot in America. It's not bad, actually. I like it. No problem with it. Well, depending on where it is, I don't mind living in it, perhaps. And depending on what's inside, I don't want a bear inside over there. But certainly, this is not, if he was basing things on precedent, he wouldn't have built something like this. Well, this is coming, hopefully, when I click. Okay, sorry. Yeah, this is the principal design that has enabled him to come up with a masterpiece. He did not imitate this one. So you need to understand what's good in past designs, and you need to depart from what's bad, basically. And I think principal designs enable you to really do that. For example, if you want to solve the data movement bottleneck, one way of doing it is to keep improving existing processor-centric designs, right? CPU is the only place you process data. You keep adding larger cache hierarchies. You keep adding prefetching mechanisms. You keep adding multi-threading mechanisms. You keep adding heavy out-of-order execution mechanisms. Yes, you're really reducing the data movement bottleneck from a performance perspective. So you're really improving the precedent. But is that the good way? Is that a good way? It's good to ask that question, basically. Is that a principled way? It's employing some principle, no question about that. The principle is processor-centric design, which has been around for decades and decades. But if you actually fundamentally think what the problem is and come up with a principled solution that targets the problem, I think it will be obvious that something else should be done. And one of the options is really to process the data where the data is, right? That's why we're going to talk about data-centric computation, near-memory processing, in-memory processing. And I think from the perspective of the trade-offs we're in, that's a much more appropriate principle to employ in the design of the computing system to reduce the data movement bottleneck compared to a processor-centric design that you keep expanding and making more complex to tolerate the data movement latency. Okay, we're going to talk more about that, but I think this hopefully clarifies what I mean by principle versus precedent. You need principles to solve the real problem as opposed to sticking to the precedent. Of course, the cost of sticking to the precedent, the status quo, is always lower. It's always easier. There's always people who would like to stick to what it is, right? They will say, okay, I don't want to change my software. I don't want to change my hardware. I don't want to change anything. So let's stick to the precedent. But that's not the way of progress. The way of progress is really changing the way we do things. That's why I like using these examples from architecture, right? These architects could have said, okay, I'm going to repeat what this person did. They didn't. Or I'm going to slightly extend what this person did. They didn't. They came up with principles that completely changed the system, let's say. And this is the principle of Calatrava. It's organic architecture. And you can see that it's a philosophy of architecture which promotes harmony between human habitation and the natural world through design approaches so sympathetic and well integrated with its site that buildings, furnishings, and surroundings become part of a unified, interrelated composition. Okay, falling water is an important one, but there are other examples of it actually that you can see. And I like this beautiful picture. I have my own pictures also. Maybe I will get a chance to find them and upload them. Okay, let's see. I don't know why this is taking too long. Okay, so I think that brings me, I've kind of covered this, but major high-level goals of this course is really to understand the principles and principles that should be applied to solve a particular problem, because principles can change also, right? If you're bound by computation, maybe being processor-centric is a good idea. But if you're bound by data access, then maybe being data-centric is a better idea, right? So understanding the principles and how to apply them is important. Understanding the precedents is also equally important so that you can understand what are the problems with existing systems and what you should apply to solve, what principles should you apply to solve what problems. And based on such understanding, hopefully we will enable you to evaluate trade-offs of different designs and ideas, and enable you to develop principled designs, enable you to develop, hopefully, even more novel and out-of-the-box designs. And I think that should really be the goal of education at a university, right? Again, university is not just about teaching what exists, in my opinion. It's also about developing skills that enable you to do something better in the world. And my goal in this course is really, hopefully, by examples at least, at the very least, let's say, and also by practical hands-on exercises to enable you to appreciate both the principles and precedents, but also go more and to think new ideas, to hopefully develop new out-of-the-box designs, right? Otherwise, I think the vision of a university cannot be accomplished fully. Okay, the focus we have is, as I said, on principles, precedents, and how to use them for new designs, and in computer architecture, clearly, right? We're focusing on computer architecture, but please remember this lecture as well. It's not just computer architecture that we're dealing with. Hopefully, this will be useful for you in whatever you choose to do in the future. Okay, this is my PhD advisor, actually, and I'm going to copy his slide and make it more complicated. But I like this mindset that he shows. Basically, the role of the architect is to look everywhere. You need to look backward, which is precedents. You need to look forward, which is you need to listen to the dreamers, applications, what's coming next in systems, let's say, and in applications. You need to look up, understand the nature of the problems, and you need to look down, and you need to predict the future of the technology so that you can take advantage of it. This is essentially my rephrasing of what he said. You need to look backward to the past so that you can understand trade-offs and designs, upsides, downsides, past workloads, analyze and evaluate the past. You look forward to the future, be the dreamer and create new designs, and also listen to the dreamers. Basically, I think progress happens because of these dreamers. Progress never happens people saying, oh, I like the way things are. Progress happens only by those who really question the status quo and they say, okay, I don't like how it is. I'm going to change it. Or I need something new, or people need something new, and this is how I'm going to enable, right? So that's how you push the state of the art, and that's how you can evaluate new design choices. That's what looking forward means. And looking up is understanding important problems and their nature at the higher end of the computing stack. And that enables you to develop architectures and ideas to solve important problems. And looking down is equally important, which is again, top and bottom, right? That we discussed. Bottom is always devices and technology. That enables you to understand the capabilities and evolution of the underlying technology, and also the revolutions that are happening in the devices, for example. And this enables you to predict and adapt to the future of the technology, because usually you're designing for N years ahead. Maybe your system will be used 20 years down the road. And that way you can enable the future technology. Okay, so the takeaways, I think, being an architect is not easy. Maybe that's not the best takeaway, but it requires effort, basically, to consider many things in designing a new system. Also, it requires the development of a good intuition and insight and critical analysis skills of ideas and trade-offs. And I think hopefully we will achieve that with the discussions and trade-off analyses that we will have in this course. But I believe it's very much fun. It can be very rewarding because you can really truly enables new future systems. And it also enables a great future for maybe you and everyone else. For example, many scientific and everyday life innovations would not have been possible without architectural innovation that have enabled very high performance systems. I think this is, there's no question about that. For example, the machine learning revolution was enabled by GPUs. And GPUs required a lot of hard work, a lot of considerations. Right now, machine learning revolution is being pushed by machine learning accelerators and processing in memory designs, etc. But again, I don't want to focus too much on machine learning. I feel that, yes, it's an important application today, and it will be an important application in the future, but that's not the only application, right? So there could be a lot more. Again, weather modeling is another example over here, but you can come up with many of the other examples like your mobile phones, self-driving vehicles, which are still looming in the horizon, and who knows what else, right? So hopefully this course will enable you to become a good computer architect and understand all of the trade-offs and come up with new designs. So this is another perspective of computer architecture. Like you have at the higher level computing systems, hopefully a course many of you have taken. This is programmers' view of how a computer system works. And at the bottom layer, you have digital design, logic, and devices. You have digital logic at a model of computation. That's the hardware designer's view of how a computer system works. So we're going to cover what happens in between, but we're also going to touch upon these other parts as well. But this is really what a computer architecture at the core is about. Of course, we're going to take a bigger approach, a broader approach. But basically, even what happens in between, like architects, microarchitects' view, is how to design a computer that meets system design goals while taking advantage of the underlying technology and digital logic, right? So choices you make in that design critically affect both the software programmer as well as the hardware designer, because you're in the middle, basically. You're interacting with the higher level software stack and system stack. You're interacting with the lower level at the logic and devices layer. So choices you make actually really affect both the software programmer and the hardware designer. And keep this in mind. That's why architecture is at a special place. If you're changing algorithms, for example, you're not affecting hardware as much from if you don't have the computer architecture perspective that I'm mentioning, right? When we change algorithms, for example, today, you may also need to change the hardware or adapt the algorithms to the hardware. But sometimes there's research that's done that completely change the algorithms without considering the hardware, and they may not be a good fit for future hardware, right? So keep that in mind as well. So the choices you make critically affect both the higher level as well as the lower level. Okay, I think this brings me to levels of transformation which we discussed, but I also want to mention some things about Richard Hamming, whom you're reading, hopefully. How many people have started reading the transcript that I asked you to read? Oh, okay, that's great. Are you enjoying it? Okay, I see. I see. Okay, I see a lot of hands. That's great, actually. Cool. I see hands on Zoom also, by the way. I heard a very comment. That's good. It was a good idea to assign. But Richard Hamming also said the purpose of computing is to gain insight, not numbers, let's say. Well, I think I've shown you. Well, I think I've shown you a picture of Hamming. This is him. But levels of transform, and we gain and generate insight by solving problems. And how do we ensure problems are solved by electrons? Basically, we go through the levels of transformation. There's a hand I see on Zoom. Does somebody want to ask a question, or does that remain because of because you raised your hand earlier? Okay, I see hand disappeared, so I'm assuming that's not a question at this point. Okay, so I'm not going to go through the levels of transformation over here. I'm going to just leave this slide because we discussed this earlier. But you can see the precise definitions of what an algorithm is and what instruction set architecture is, which is interface and contract between software and the hardware. This is what the programmer assumes hardware will satisfy. Microarchitecture is an implementation of the ISA, and digital logic is building blocks of the microarchitecture. And then you have devices, etc. But basically, we're going to take a broader approach than the regular architecture approach. We're going to really take the full stack approach in this course. But I think before we go into that, I will also mention Hamming. Since you're reading about Hamming, I would also recommend some other works by Hamming. This is the work that really started coding theory and error detecting and error correcting codes that Hamming invented. It introduced the concept of Hamming distance. How many people know about Hamming distance? Okay, I see some hands. I will define it right now. I think many people know about it. If you don't know about it, it's easy to learn. But basically, it's the number of locations in which the corresponding symbols of two equal length strings is different. Okay, so hopefully it's easy. So I don't know. Maybe I'll try to use my. Let's see if you can hear me. We should test this also. Whiteboard. Can you see my whiteboard over here? Okay. So for example, well, maybe that's not a good choice. Green and black. These are two equal length strings, and the Hamming distance between them is 5, meaning they are different in every location of each string, right? Okay. Well, if you change black, if you want to compare black and bloom, for example, now the Hamming distance between them is 3 because they're different in these 3 over here. Yes, they're equal in the first 2. Okay, so it's a very simple concept. Basically, it's the distance between 2 different, let's say, strings. Okay, I'll go back to over here. I hope that was easy to see. I don't know. Was it okay? Okay, that's good. So basically, based on this concept of Hamming distance, he developed a theory of codes that is used for error detection and correction. And this has had a lot of impact on the field. And Hamming, for this very reason, won the Turing Award, actually. So what you're reading is really a transcript of the talk that was given by someone who has made really seminal contributions to the field. And he was also a very principled person. I will also mention that in a little bit. So this is what you're reading. That's good. I would also recommend, if you have time. These are actually some precious lectures that are delivered by Hamming in 1995. I did not assign any of these because your transcript is a little bit different from these lectures. Even though there's a lecture that's titled You and Your Research at the end over here, the transcript is really scattered around these lectures, if you will, over here. And I would recommend these lectures quite a bit because he builds a lot of insight into how to think and how to, he doesn't go into technical topics, basically. He really talks about how you can be a better scientist and researcher and how you can succeed. He even talks about, for example, speaking skills and discussion skills and how to really approach problems and how to pick important problems, etc. So I would really recommend these lectures. They have a lot of insight into them. Okay, so I think it's also good to question this levels of transformation that I showed you earlier. I showed a monolithic stack, right? But one thing that it's always good to be a critical thinker, in my opinion. If you see a stack like that, you should also ask the question, okay, where's the user here? Maybe the most important thing is the user, right? User who uses the computer, right? Or user who programs the computer. Basically, user interacts with the stack at many different levels. And once you incorporate the user into the stack, it becomes really interesting, I think. User can be providing the problem. It could be interesting, the problem. User can be providing the algorithm. User can be providing the program. User can be interacting with the runtime system directly. User can be potentially interacting with the ISA and maybe even the microarchitecture, who knows? So this brings us to the thinking that maybe the entire stack should be optimized for the user, right? So I think it's good to question what the stack that I showed you earlier doesn't take into account. And I think user is one example of it. In the end, it's about the users using the computers. It's not just the problems being solved, because problems are actually also provided by the users, right? Okay, let me quickly talk about levels of transformation a little bit more. They create abstractions, basically. They enable you to limit your knowledge to one layer, potentially. This could be good or bad. So a higher level, what is an abstraction? A higher level only needs to know about the interface to the lower level, not how the lower level is implemented. Okay, so for example, a high-level language programmer does not really need to know what the ISA is and how a computer executes instructions. And this abstraction improves productivity clearly. You don't need to worry about the decisions made in underlying levels. That's great. For example, programming in Java is easier compared to programming in C, compared to programming in assembly, compared to programming in binary, zeros and ones, compared to programming by specifying the control signals of each transistor every single cycle. Clearly, having a higher level abstraction is much better, right? But there are cases where this is not much better. Sometimes you want to break the abstraction layers. As long as everything goes well, not knowing what happens underneath or above is not a problem. But what if the program you wrote is running very slowly? What if it doesn't run correctly? What if it consumes too much energy? What if your system shuts down and you have no idea why? And what if someone compromised your system, like with a RowHammer attack or with Meltdown and Spectre, and you have no idea how? So in this case, then you really need to know what's happening across the stack. Also, what if the hardware you designed is too hard to program? What if the hardware you designed is too slow because it doesn't provide the right primitives to the software? This is the hardware perspective, if you will. If you don't know about what's going on at the higher levels of the stack, you may have no idea in terms of how to solve the problem. And what if you want to design a much more efficient and higher performance system, entire computing system, like a machine learning accelerator, like a genomics accelerator? Then you really need to cross the layers. That's why crossing the abstraction layer is important. And hopefully in this course, we will cross the abstraction layers a lot. We'd like to understand how a platform works underneath the software layer and how decisions made in hardware affect the software and the programmer. And also vice versa, I should say, how decisions made in software affect the hardware as well. And hopefully we will enable you to be comfortable in making design and optimization decisions that cross the boundaries of different layers and system components. So even though abstraction layers are good for productivity, if you're really a good computer system designer, you should be able to cross the computer, those abstraction layers, and you should be able to move comfortably between the layers. You cannot say, okay, I'm going to focus on the logic layer and I don't care about anything else. That's unfortunately not doable today. Maybe there was a time in the past, a long time ago, that was possible, but today I think we're not there. So we're going to show a lot of examples in this course. I'll just quickly overview some examples. We're going to talk about multi-core systems, for example, issues in interference. other issues in cache design, etc., memory controller design especially. We're going to talk about, I'm not going to cover all of these. Maybe in the next lecture we will start. Certainly we're going to talk about DRAM, memory. In fact, we're going to start a lot with memory and memory controllers, and then we'll move to potentially computation. If you're really interested in computation paradigms, digital design and computer architecture courses may be useful for you to look into. But in this course, since memory is the bigger bottleneck, we're going to start with understanding the memory and its relation to computation, of course. I mean, we're never going to ignore computation, because computation needs to be done, right? It's important, but we need to understand the memory also. So this is something we'll look into. We're going to cross the abstraction layers a lot in all of these things that we touch. Clearly, RowHammer, we're going to examine more. We're going to cross the abstraction layers. We're going to talk about hardware solutions, potentially software solutions, memory controller solutions, DRAM solutions, etc. And we're going to talk about the data moment problem. I'm picking examples also that we have seen and we have not seen. Clearly, we've talked about data moment, and this also requires crossing the abstraction layers to solve the problem. I actually had one more over here, but I don't know what happened. Oh, okay, yeah, there you go. Somehow I skipped the slide because I don't know why my computer is doing this way. It's going a bit too fast and too slow at the same time. Okay, yeah, memory refresh is another example that we will cover, because refresh of memory devices is becoming a bigger problem as technology scaling makes them smaller and more vulnerable to retention errors. So memory is getting refreshed more frequently, and this is causing a lot of energy problems as well as throughput problems, and we're going to cover that also in the next lectures. But again, you need to cross the abstraction layers and think across the stack and think in a principled manner to actually solve these problems, and hopefully we will see examples of it. Okay, I think that brings me to the end, which is good. I'm happy to take any questions. Yes, please go ahead in the room.
So one thing about the abstraction layers, I guess, is that means that you're gonna have to understand things in much greater depth. And so I guess the first question is like, to what extent? And the second question is how. So for the first one, in more detail, to go up means you have to go into computer science, and to go down means you have to go into electrical engineering. There's just so much information that you hear that, people who like do a whole degree, like a whole master's and bachelor's in CS, like some people still say these guys don't know CS. So like, I guess like, to what extent do we have to know these different abstraction layers?
Yeah, I mean, that's a good question. And yeah, it's not easy. I'm not going to argue that it's going to be easy, right? Yeah, I mean, to some extent, you're right. I think of it as all like a continuum, right? Computer science, maybe, yeah, sure, at this level, but also there's a lot of computer engineering over here. And maybe this is closer to electrical engineering and physics. Sure, no question about that. To what extent is a good question. Basically, you don't necessarily need to know everything, right, at the above layers. But you need to know, for example, how the decision that you make in a machine learning accelerator, let's say you're designing hardware, you need to know how the decision affects the programmability of that accelerator, for example. If something makes the programmability extremely hard so that your accelerator is not going to be usable easily, you either need to find a way of solving that problem, develop the software stack for it so that it becomes easy to program or enable the programmers to use it, or you need to change some design decisions to make it easier to program. So you don't have to know everything that happens in algorithms, for example, right? In a sense, this is more, I have a problem to solve, I'm designing something, and you need to make a decision as to how it affects people at the top and how it affects people at the bottom. I don't know if that's clear. We will see examples of it, but I'm not suggesting you should know everything that happens everywhere, right? That's not what I'm suggesting. I'm suggesting that whenever you design something, you should be aware of the potential consequences of the decisions that you make and the trade-offs that you make, both at the higher levels and the lower levels. And this doesn't have to be accomplished just by yourself, right? You can actually work with other people to understand this also, right? In fact, that's what happens in many accelerator designs today. When people design accelerators, they consult people who are going to write software for those accelerators also. And it's really a across the system design where they do back and forth in terms of, okay, if I make this design choice, can you make use of it? If I make this design choice, is it going to make your life harder? Or tell me something I can do in my hardware that is going to make your life easier in terms of programming, right? So this is the sort of thing that I am suggesting. Of course, I'm giving you a particular example of accelerators over here. There could be other things, but in general, whenever you design something at any layer, it's good to consider the consequences at different layers.
Wait, I think that makes sense. So like,
Okay.
yeah, because so the question then becomes, as a guy in the middle, what advances on the bottom do you rely on? And then how do your decisions affect things above you? And this seems to be more in the field of like practical than like more of like the hands-on field than the purely theoretical fields. And so you get this knowledge by, I guess, working with practitioners is what you're suggesting.
Well, partially working with practitioners, but also partially, I think, getting into this mindset where you keep evaluating the effects of the ideas using some of the metrics that you wouldn't normally consider. For example, if you're not considering higher levels of the stack, right? For example, let me give you an example. If you're a hardware designer, traditionally, what you care about is how much area does my logic consume? How fast is it? And more recently, what is the energy, right? That's it, 3 metrics. Or also, does it work, of course, right? Is it functionally correct? You wouldn't normally consider metrics such as, oh, how is this going to be programmed? Is it going to be easy or is it going to be hard? What are the reliability effects on the higher levels of the software stack? So I'm suggesting basically you need to develop a mindset and a principled mindset to consider these other metrics that would affect higher levels of the software stack or lower levels of the software stack, lower levels of the hardware stack. Does that make sense?
Yeah, that makes sense. Thank you.
Okay, cool. Okay, excellent. Okay, I think we're already out of time. So if people need to go somewhere, please feel free to go. But I think there are some questions, so maybe I will handle them. Let's see. Could we get some more details on the grade for this course put together at the end? You can find that in the course catalog, as somebody on Zoom answered. I was planning to also cover course logistics in 10 minutes, but I'm not going to do that given that we're already out of time right now. But essentially, we're going to follow the course catalog. I think if I remember correctly, maybe I will bring up just that slide since that question was asked. Let's see. I will share if I can find my other PowerPoint. Yeah, course logistics slide where we cover the grade. I hope grades are not going to be the most important thing you consider, but I understand also people like thinking about grades. Okay, basically this is just a summary of the answer that you can also find online. Basically, we have lab assignments that consist of half of the grade. We're going to have probably around 5 lab assignments. We have final exam, 30%, which we reduced from 35% because I don't want this to be an exam-oriented course in general. And we have homeworks that are about 20% basically. And that's how it's computed. And there are many extra credit possibilities, as I mentioned yesterday, both all in homeworks, labs, as well as exam. Basically, there will be bonus points. So I think doing well in this course, even though it's a hard course, doing well and getting a good grade in this course is not that difficult in the sense that you have many opportunities to actually do the extra credits. So again, as I mentioned yesterday, it's always good to know your strengths and weaknesses. For example, if you're not a good exam taker, I would probably put my effort into doing more extra credits because those will directly affect your grade. And extra credits may be easier to do, clearly, because you don't have the exam pressure, right, at that point in time. Or I would focus on the lab assignments. I think lab assignments are really good because you can learn hands-on, as we will discuss in the course logistics at some point. Let's see. How much computer science? Another question is how much computer science engineering is this course and how much of it is EE? Seeing as there are hardly any CS students like me taking this course, is it perhaps easier if you're from an EE background? So I think it's really in the middle, I would say. I would say this is really a computer engineering course. And we will delve into both circuits, and we will also delve into software. So it's really in the middle. Like what I said earlier is true. And I don't think what you said is correct. So when I look at EDOS, for example, the distribution of students in the course, traditionally it has been 1/3 to 1/2 is computer science students, and I think that's still true. Okay, there's another question. What about face-to-face interviews? I think we'll get back to you on how the interviews will be conducted related to labs. And I think TAs will handle that. How do you submit the paper reviews? Again, I think you will get links related to that in your homework. The homework will be released today, so you will see that. What are extra credits is another question. You will see that also, I think. Basically, reviewing some extra papers is extra credits, meaning if you do that review, you will get some more points, which will directly affect your final grade. And that's true for lab assignments also. There's an extra credit portion. You don't have to do it for finishing the lab, but if you do it, then you will get some extra points that will directly affect your final grade. Okay, I think I answered all of the questions on Zoom. There's one more question. Yeah, go ahead, please.
Just to clarify the concept of principles, would you say it's very similar to like the first principles, which is like starting from an observable truth and then working off of that, rather than, and the opposite would be, I guess, the precedent base, which is just doing not because of any observable truth, or I guess the only observable truth being that other people are doing it.
Yeah, I think there's some analogy over there. Yes, I mean certainly. Yeah, I would say that's a good analogy actually. Basically, when I think of observable truth, it's really the truth, the problem that I mentioned, right? For example, the data shows that the data movement is a huge bottleneck. Overwhelming majority of the performance and energy goes to data movement. That's kind of your observable truth, I think, in this perspective. Whereas precedent is other people are doing something which may not be consistent with solving that observable problem or observable truth as you put it. So I think, yes, I think that's a good analogy.
Great, thanks.
Sure. Okay. Okay, it seems like we're done. I don't see any other questions. I don't see any hands. And I'm done with slides, as you can see. So that sounds good. Let's call it a day. Hopefully I will see you all next week, next Thursday, in the next lecture, where we will start with more detail on the memory systems and hopefully apply some of the things that we discussed in terms of principles, trade-offs, trade-off analyses to what we see. Okay, take care. Have a good weekend. Stay safe and well.